Good afternoon. Good afternoon, everyone. Welcome to the class. I hope we have understood basics of number systems. We have discussed. Then we have seen how to calculate base values for given equation and how to convert from one number system to another number system. I hope everything is fine with audio and video. You are able to see my screen. Yes. Thank you. Yes, yes, yes. Right, fine. Thank you. Thank you for your response. Right. Yes, we have discussed basics of number systems, how to convert from one number system to another number system. Then we have seen how to calculate base values for given equation. Right, by giving an equation, they're asking you to find possible base values which can satisfy given equation. In that, assuming a variable for base, converting to decimal, using decimal manipulations, we are solving the equation. Then the values we are getting for base, which is unknown variable, we are validating. Finally, what we have done? Validating. So in that validation, what we need to check? The base we are considering is greater than all the digits or not. Next thing is functionally it is satisfying or not in that number system. That's what we need to check. What is it here? In validation, we are checking whether all the digits in the equation are lesser than base value or not. And next, whether it is true, the equation given is true or not, we are verifying. Again, we are using different methods to validate that we have seen with examples. Now, let me give you one more question. Find number of valid solutions of x and y which can satisfy the following equation. Question is find number of valid solutions of x and y which can satisfy the given equation. It is not asked what is the values of x and y. How many sets of x and y are valid for given equation? The question is 4,3 base 8 is equals to x0 base y. This is a given question. Equation is given. We need to find possible sets of x and y. How many possible sets are valid? That's what we need to calculate. That is given equation. Then, as we are comfortable in decimal number system, always we prefer to use a decimal number system. Then here 8 power 0, 8 power 1 are weights to calculate decimal equivalent of 4,3 base 8. And again, y power 0, y power 1 are weights for this number because y is the base. Y is the base. So with that base, the weights, if you are observing y power 0, y power 1, then what should I do? 4 8 32 plus 3 into 8 power 0 is 3 is equals to x into y plus 0 into y power 0 is 0. Then what we are getting here? Xy is equals to 35. What do you mean by this? X into y equals to 35. What are x and y values which can satisfy this equation? X and y integers which can satisfy given equation. 1, 35, 35, 1, 5, 7, 7 and 5. These are x and y values which can satisfy given equation. What is the equation? X into y equals 35 equation is satisfied with x and y sets specified. In these, let us validate. Right. So now, which are valid in this, we need to verify. 135. Can I use 135? Yes. Why? 35 is the base. Right. 135. That means base is 35. Decimal equivalent of a symbol is 1 is accepted. So don't have an opinion that base should be till 16 only. Nowhere it is mentioned. If I use 20 symbols, base can be 20. If I use 30 symbol, base can be 30. If I use 100 symbol, base can be 100. But we need to understand one important thing here. Please focus on my words. Try to understand this. What is it here? Already we confirmed base cannot be 0. Base cannot be negatives. And also base cannot be fractions. One more thing we need to consider. Once again, let me repeat once again. Please understand correctly. Base cannot be negative, confirmed. Base cannot be 0, confirmed. Base cannot be fractions, that is confirmed. And one more thing we need to understand. Base can be 1 or not. What do you mean by base 1? I'm using only one symbol. If I use only one symbol, there is default as 0, which is representing 0 quantity. That means that 0 is saying that nothing is there. For example, no one is there in the class. That is 0. 0 quantity. To differentiate non-zero quantity from 0 quantity, we need one more symbol other than 0. Try to understand once again. Base, can it be 1 or not, we are discussing. So if I use base is 1, that one symbol 0 is compulsory in every number system. That means without using another symbol, I cannot say there is a quantity. 0 is default in any number system, that is representing 0 quantity. Nothing is there. But we need one more symbol other than 0 to say something is there which is non-zero quantity. That means base 1 is also not possible. Base 2, yes. Already we have been discussing binary. It is having 2 symbols. Yes, 0 and 1 sufficient to represent a quantity. The possibilities I'm confirming. Base cannot be negative. Base cannot be 0. Base cannot be 1. Base cannot be fractions. It must be a positive integer which is 2 and above. Already we discussed this point. Base cannot be negative because it cannot be realizable without using symbol. By giving back, how can I represent a number? Right? Someone is raising hands. Please have patience. I'll give time. I will answer everyone's doubts. Please remember the frame numbers. I'm there to help you. Please wait a minute. I will be repeating again and again. Focus on my words. I'm not concluding with one statement. I'll be repeating again and again. So first explanation, try to understand. The second explanation, mostly you need to understand. Third explanation, if required, that will be given with your request. Right? So try to focus on my words. What we have been discussing, possibilities of base in general, not with this question. I'm not talking with respect to this question. I'm discussing in general. In general, I'm talking in general, base cannot be negative, base cannot be fraction, base cannot be 0, base cannot be 1 also. The reason for not having base 1 is one symbol is default 0 in every number system. That is representing zero quantity, which is saying that nothing is there or no one is there. That means something is there other than zero quantity. For that, we need one more symbol other than 0. That means 0 is zero quantity. To represent non-zero quantity, at least one more symbol is required. That means it can be two symbols sufficient to represent a quantity, to represent a number. Minimum two symbols is compulsory. The reason is 0 is default. With 0, I cannot convey the quantity which is non-zero quantity. To differentiate zero quantity and non-zero quantity, at least we need two symbols. I hope you are understanding now. Yes, in general, I'm talking, not with respect to this question. Don't analyze with respect to this question. I'm talking in general, what is the possibility, right? Right. 135, we confirmed it is possible because base is 35, decimal equivalent of a symbol is 1, which is accepted. It is accepted. There won't be any doubt. Now 35 1. Just now I discussed base 1 is not possible. Even though base 1 is possible, 35 is decimal equivalent of a symbol. How can I accept that? The first thing is base 1 is not possible. Assume it may be possible somehow. Even though it is possible, symbol X is getting value greater than base value. How is it possible? Impossible. So the decimal equivalents of symbols we are using must be lesser than base values. Already we discussed this yesterday. The decimal equivalents of symbols is ranging from 0 to r minus 1 in radix r. In a number system with radix r, the possible symbols are 0 to r minus 1 only. Then first thing is base 1 is not possible. Even though base 1 is possible somehow, how can I accept a decimal equivalent of a symbol is 35 in that base 1? It is impossible. Now 5 7. Try to understand this one also. 5 7. What do you mean by this? Base is 7. Base is 7. And decimal equivalent of a symbol is 5. Is it acceptable? Yes. Base is 7. Decimal equivalent of a symbol is 5. Is acceptable. Now 7 5, which is indicating y is 5 means base is 5. And decimal equivalent of a symbol is 7. Can we accept that? No. In base 5, it is possible to have 0, 1, 2, 3, 4 only. In base 5, it is possible to have 0 to 4 only. Then 7 is not possible in base 5. Yes. The number of valid solutions for this question is 2. Answer for this question is 2. The question is what? We need to find number of valid solutions or sets of x and y which can satisfy given equation. For that, what we have done? We have tried to calculate x and y values which are possible. Then we have validated. Final conclusion is we have only two sets of x and y. That is 135, 5 and 7. Any doubt in this? Is it clear? I'm moving to next slide. Right. Okay. Why 7 and 5 is not valid? If you are getting a doubt, let me repeat that. What do you mean by 7 and 5? X is 7, Y is 5. Y is 5 is indicating base is 5. When base is 5, the valid symbols are 0, 1, 2, 3, 4. But you are saying that X value is 7. When Y equals to 5, X is 7. Then only X into Y equals 35 is valid. So, if Y equals to 5 is indicating base is 5 and a symbol with decimal equivalent is 7, do you accept that? No. That is the reason it is invalid. 5 and 7, yes, accepting because base is 7, X is 5. So in base 7, it can have 0 to 6. Valid. Please don't raise the hands. I'll give you chance to ask doubts at the end. Until that, please wait and remember your slide number or frame number. So just remember where you have doubts, in which frame you have doubts. Don't forget to remember that. Again, question is same. What is that question? Find number of valid solutions of X and Y which can satisfy the given equation. Find number of valid solutions of X and Y right? Then what can I do? So here 5 power 0, 5 power 1, 5 power 2 are weights. Here y power 0, y power 1. Then 1 into 5 square plus 2 into 5 plus 3 into 5 power 0 is equals to x into y plus 8 into y power 0. Then 25 plus 10 plus 3 is equals to xy plus 8. Then 38 is equals to xy plus 8. Then xy is equals to 30. Xy is equals to 30. Then what are x and y values which can give x into y equals 30? X, y. 1, 30, 30, 1, 2, 15, 15, 2, 3, 10, 10, 3, 5, 6, 6, 5. These are possible integers which can give x into y equals to 30. Right. These are possible values of x and y which can give x into y equals 30. In these, how many are valid we need to verify. 130 valid. Yes, base is 30. Decimal equivalent of a symbol is 1. Accepted. 31. Base 1. First thing is, it is not acceptable, right? 215. Yes, base is 15. Decimal equivalent of a symbol is a 2. Accepted. 15 2. In base 2, how can I get a symbol with a decimal equivalent 15, which is impossible. 310. 310. Right? Base 10, decimal equivalent of a symbol is 3, accepted. 10 3. Not valid, because in base 3, how can I get a symbol with the decimal equivalent is 10? It's not valid. 5 6. So in base 6, decimal equivalent of a symbol is 5, accepted. 6 5. In base 5, I cannot get a symbol with the decimal equivalent is 6. It is not possible. Finally, number of valid solutions is 4, which is again wrong. Why it is wrong? Let us verify. What is it here? X8 base Y. Then what we are observing? Y must be greater than X or X must be less than Y. Not only this, Y must be greater than 8 also. Y must be greater than X, Y must be greater than 8. In the previous example, as the other digit was 0, we were checking only XY condition. But in this example, we have two digits. Base must be greater than these two. So Y must be greater than X, Y must be greater than 8. Then 5 6 is not valid, because for one condition is satisfying, second condition is not satisfying. What is that? Y must be greater than X, Y must be greater than 8. These two are. So finally, how many valid solutions? 3 valid solutions. Yes. Now everyone is able to understand and observing in right way. Number of valid solutions is now 3. Once again, the condition we need to check. The base must be greater than all the digits we are using. That means Y must be greater than X, Y must be greater than 8 also. Then only it is acceptable. Right? Y must be, right? What is Y? Base. Base of a number system. Base of a number system must be greater than X, and base of number system must be greater than 8, because it is provided two digits. In the previous example, if you are observing, Y is positive integer. If it is greater than X, obviously it will be greater than 0. Right? That is the reason one condition was sufficient, Y greater than X. Y greater than X, Y must be greater than 0. So second condition is not that much serious in this. But coming to this, what is it here? Y must be greater than X, Y must be greater than 8. So Y is greater than X and Y is greater than 8 is satisfied in these three. Coming to this one, 5 6, only one condition is satisfied. What is that? Y greater than X. Second condition is what? Y greater than 8 is not satisfied. Why we are considering 6? 6 is not valid here. Base cannot be 6. Don't go with only one symbol. That is the reason, right? 5 6 is also not valid. Yeah. With this, right, I would like to convey some more words about competitive exam preparation. Please understand these in a positive way, not to scare you. Simply, how to prepare is very important, because after writing exam, if you are realizing it is no use, that is the reason always I suggest my students, please find your mistakes before going to final exam. If you are not solving these type of questions, if a question is given in the GATE exam, or ESC. If you are doing a mistake and rectifying your mistake after coming out of exam hall, will it be useful? No. There is a reason. Practice is very important. Concept is understood. Have given the statements also. Concept is already given. What is the concept we are using? Decimal equivalence of symbols is ranging from 0 to r minus 1 in radix r. There is only statement. Statement is given. Concept is given. How to apply that? We can get by solving questions only. It looks like same as the previous question. Yes or no? Here we have observed only y must be greater than x, because other digit was 0. If you solve this question, if you are remembering the procedure we have used, there is a possibility for doing mistakes here. Most of you have answered it as 4. I can see in the messages. The reason is you are following a method and don't expect similar question will be given in the exam. There will be a small change in the question. Looks like same, but not same. That's what we need to observe and understand about competitive exams. Looks like same. A small change will be there in the question. So whether we are understanding concepts or not, they are checking. They are not checking that whether we are remembering all the procedures for previous year's questions. No, they want to check your knowledge and your observation. Take it in a positive way. Don't get scared. A simple thing we need to understand, because we want to get a result of this coaching. There is a reason I'm suggesting you have some confidence and proceed to practice with different types of questions. Srikanth, wait, why are you raising your hand? Where is the doubt? I will address your doubts later. Please. Right. Srikanth. Medaboyina Srikanth. Right. Fine. So, many are preparing for exam. Very few have been succeeding. Why? By adding statements, remembering procedures, remembering shortcuts, and if you are getting similar questions, it is fine. Otherwise, it will be a bad choice. So, when you are choosing this path, I suggest you dedicate yourself. There will be better life. Right? So, take it in a positive way, because we should not feel after getting result. If you are worrying now, if you are bothered now, if you are feeling low now, not a problem. Till the exam, there will be struggles. Accept this 1 year. Yes, then obviously there will be better result. If you are not ready to accept these things, ups and downs, and all these, if you are not accepting, you need to accept at the end after exam. Please understand these things, because I've been observing my students from many years, what they have been doing mistakes. There is a reason I'm suggesting, don't follow any procedures or shortcuts. Understand the concepts in a right way. How you are applying that each and every concept we are discussing in given question is giving better result. Right? Now we are not here for procedures and shortcuts. We are here for concepts, because the level of questions is different nowadays. Right? So, yeah. moving to next topic. Yes. Next topic is complements. Next topic is complements. What are the complements we have? 2's complement and 1's complements of a binary number system. 10's complements and 9's complements of decimal number system. 8's complements and 7's complements of octal number system. R's complements and R minus 1's complements of a number system with radix R. That we name it as a one is a radix complements, which we say R's complements. Second one is a diminished radix complements. We say R minus 1's complements. We have two types of complements, radix complements and diminished radix complements. Before proceeding to this, I would like to ask one more thing. Is this fine about slide, font, the way I'm writing, audio and video? With respect to slide, font, color I'm using, audio and video. Please respond for this. Thank you, thank you, thank you. Thank you, thank you. Many are responding. Thank you, thank you, thank you, thank you. Right. Very good. Right. So number is in radix R. We have two types of complements. Two types of complements. One is a radix complements. Second one is a diminished radix complements. We can say R's complements and R minus 1's complements. Let me say a number n in radix R like this. Let me say the dn minus 1, dn minus 2, so and so, d1, d0. Point d minus 1, d minus 2, d minus m. What are the d digits we are using? So integer part and fraction part. Integer part and fraction part. So in integer part, how many digits we have? N digits. 0 to n minus 1. It is n digits. What about fraction part? M digits. We have m digits in fraction part. 1 to m digits. So number of digits in integer part is n, number of digits in fraction part is m, right? Number n is in radix R. Then how to get R's complement is R power n minus given number for n non-zeros. If n given number is itself all zeros, R's complement also all zeros. What is it here? Small n is number of digits we have in integer part. Capital N is a given number in radix R. To get R's complement, the formula is R power n minus given number. if it is a non-zeros. If given number itself is all zeros, then again complement is all zeros. Again complements is all zeros. If r minus 1's complements is r power n minus r power minus m minus given. Irrespective of either it is all zeros or non-zeros, what is it here? R power n minus r power minus m minus given number. This is r minus 1's complements of number in radix r. And these are the procedure, but we don't use these procedures in our calculations. What is that we use to get complements? Let us see. Wait, Manisha. I'll give you a chance, right? Wait. So, what should we do? How to get complements? Let us see. This is a procedural calculation of these complements. But directly we are using alternative method to get complements. Let us see what is the alternative method for getting complements. Right? So, instead of using these formulas, observing n and m and so, what we can say, to get r minus 1's complement of a number in radix r, to get r minus 1's complement of a number in radix r, subtract all the digits from r minus 1. Subtract all the digits from r minus 1. Once again, to get r minus 1's complement of a number which is in radix r. Base of the number system is r. We are trying to get r minus 1's complement. When you are trying to get r minus 1's complement of a number in radix r, subtract all the digits from r minus 1. To get r's complement of same number is nothing but adding 1 to least significant digit of r minus 1's complement. Once again, to get r's complement of a number, add 1 to least significant digit of r minus 1's complement. Let me repeat these two statements once again. To get r minus 1's complement of a number in radix r, subtract all the digits from r minus 1. Second one, to get r's complement of a number in radix r, add 1 to least significant digit of r minus 1's complement. Whatever I said in the statements, I'm going to apply. We will understand more about this. Let me take some examples, then we'll understand more about these methods we are using to get complements. For example, there is a decimal number like this. That is a given number in decimal. That is given number in decimal. We want to get tens complements and nines complement of these numbers. Tens complements and nines complements of this number. Right? See, this is decimal number. We want to get nines complements and tens complements. What is decimal number? R equals to 10. Nines complements means, is it r minus 1's complements or r's complements? People are worrying about statements. That's what I'm using here. I'll repeat once again. Please wait. So, number is in radix 10. Number is in radix 10, r equals to 10. We want to get nines complements. Then what should I do? R minus 1's complement. How to get r minus 1's complement, sir? Subtract all the digits from r minus 1. What is r minus 1 in this? 9. To get 9's complements of decimal number, subtract all the digits from 9. So 9 minus 0 is 9. 9 minus 6 is 3. 9 minus 0 is 9. 9 minus 9 is 0. 9 minus 2 is 7. 9 minus 1 is 8. 9 minus 0 is 9. 9 minus 8 is 1. 9 minus 0 is 9. 9 minus 0 is 9. What is this? 9's complement of decimal number. What I'm doing here? Subtracting all the digits from r minus 1. That is the first statement I discussed. To get r minus 1's complement of a number in radix r, to get 9's complement of decimal number r equals to 10. Right? So to get 9's complement, what we mentioned? Subtract all the digits from r minus 1, which is 9 here. Subtract all the digits from 9. Let me repeat that statement once again. Get clarity. To get r minus 1's complement of a number in radix r, subtract all the digits from r minus 1 itself. Then, how to get 10's complements? It is r's complements. R equals to 10, 10's complements. Then what I mentioned, add 1 to least significant digit of 9's complement. That is r minus 1's complements. To get r's complement, add 1 to least significant digit of r minus 1's complements. Then add 1 to least significant. What is least significant? Significance of a digit is decided by weight. Least weight, least significant. Most weight, most significant. Significance is decided with respect to weight. Here, rightmost is having least weight, leftmost is having highest weight. I hope you are following. So, least significant digit, rightmost. Most significant bit, leftmost. Right? Now, 9 plus 1 is 10, 1 is carry. 1 plus 9 is 10, 1 is carry. 1 plus 1 is 2. Then here, 9, 8, 7, 0, 9, 3, 9. What is this? 10's complements. What is this, sir? 10's complements. So, you must get it out. Why are you considering zeros here, zeros here? Yes, with respect to magnitude, those zeros may not be having significance. But with respect to complements, those zeros also having significance. Don't neglect those zeros. Zeros in the left for integer part, zeros in the right for fraction part may not be having significance with respect to magnitude. But with respect to complements, those zeros also having significance. What is the importance of this? We are going to understand soon. And with that, please hold on. At this moment, blindly follow that. So, zeros in the left for integer part, zeros in the right for fraction part are not having significance with respect to magnitude. But with respect to complements, those zeros also having significance. Don't neglect those zeros while taking complements. Blindly follow this. Importance of this you can understand soon. While taking complements, even though we have zeros in the left for integer part, zeros in the right for fraction part, those zeros should not be neglected. Those zeros should be considered while taking complements. Follow this for now blindly. Right? Now, let me take an octal number. Anjaneyulu. Mr. Anjaneyulu, please wait. This is given octal number. We want to get 7's complements and 8's complements of octal number. Understand this correctly? This is an octal number. We would like to find 7's complements and 8's complements of octal number. 7's complements and 8's complements of octal. What is 7's complements? R minus 1's complements. Why? R is equals to 8. When R is equals to 8, when you are finding 7's complement, which is r minus 1's complements. Am I right? 7's complements means r minus 1's complements. Then subtract all the digits from 7. All the digits from 7. Why? R minus 1 is 7 itself. R equals to 8. R minus 1's complement. Subtract all the digits from r minus 1. What is r minus 1? 7. So 7 minus 0, 7. 7 minus 0, 7. 7 minus 1, 6. 7 minus 2, 5. 7, 0, 7, 2, 7. What is this? 7's complements. How do we get subtracting all the digits from 7 itself? How to get 8's complement? Adding 1 to least significant digit of 7's complements. Adding 1 to least significant digit of 7's complements. Now let us see what is this. 7 plus 1 is 8, right? But 8 in octal, 1, 0. R in radix R, or in base R is 1, 0. Now we are getting 8. 8 in base 8 is what? 1, 0. Yes, 0, 1 is carry. Be clear about this. 7 plus 1 is 8. 8 is not a symbol in octal. 8 is not a symbol in octal. 8 is what? 1, 0. 1 is carry, 0 is sum. 1 plus 2 is 3. Then 7, 0. Here 7, 5, 6, 7, 7. This is a 8's complements of given octal number. 8's complements of given octal number. Now, binary number. For binary number, what we have? 1's complements and 2's complements. 1's complements is R minus 1's complements. 2's complements is R's complements. Yes, 1's complement. How to get 1's complement? Subtracting from 1 itself. Because R equals to 2, we are saying that 1's complement. That means R minus 1's complements. Then what should I do? Subtract all the digits from 1. 1 minus 0 is 1. 1 minus 1 is 0. 1, 1, 0, 0, 0, 1, 0, 1, 1, 1. Subtracting from 1. If it is 0, 1 minus 0 is 1. If it is 1, 1 minus 1 is 0. Complete 2's complements of this. Adding 1 to least significant bit of 1's complement. I'm saying here bit because it is binary. When you're coming to binary, we say bits. And in general, we say digits. So 1 plus 1 is 2. In binary is 1, 0. 1 plus 1 again 2, 1, 0. 1 plus 1 again 2, 1, 0. 1 plus 0 is 1, 1, 0. Now 0, 0, 1, 1, 0, 1. This is what we get 2's complement of a given binary number. Right? So getting R minus 1's complement, subtracting all the digits from R minus 1. Getting R's complement, adding 1 to least significant digit of R minus 1's complement. Right. That is 1's complements and 2's complements of binary number. If the given number is an hexadecimal, what we will have here? 15's complements, or another name for this is what? F's complements. Remember this. 15's complements. Another name for this 15's complements is F's complements. What is this 15's complements here? R minus 1's complement. Then what should I do? Subtract all the digits from R minus 1. What is it here? 15. 15 minus 0. 15 means it is F. 15 minus 12 because C is 12. So 15 minus 12, which is 3. 15 minus 0 is F. 15 minus 9 is 6. 15 minus 15. F is 15. 0. 15 minus 2, 13, which is D. 15 minus 0 is 15 F. 15 minus 7, which is 8. 15 minus 0 is F. 15 minus 0 is F. What is this we got? 15's complements are F's complements. Now 16's complement. How to get that? Adding 1 to least significant digit of 15's complements. F plus 1. 15 plus 1, 16. 16 in hexadecimal, 1, 0. R in base R, 1, 0. 1 plus F, again 15. Plus 1, 16, which is 1, 0. 1 plus 8, 9. F, D, here 0, 6, F, 3, F. That is 16's complements of hexadecimal number. Hexadecimal number. Right. So now you can understand the statements which I was mentioning, right? What I mentioned, if number is in radix r, base r, to get r minus 1's complements, to get r minus 1's complement, subtract all the digits from r minus 1. To get r's complement of a number in radix r, adding 1 to least significant digit of r minus 1's complement. Let me repeat these two statements once again. Number is in radix r. I want to get r minus 1's complement. What we do? Subtract all the digits from r minus 1. How to get r's complements? Adding 1 to least significant digit of r minus 1's complements. These are what we discussed before taking these examples. People were worrying about statements. Now you can understand what is the statement. You can write the statements in your words also. Right? Right. Now, in these discussions so far we have done, what we observed, to get r's complements, we are depending on r minus 1's complements. Am I right? In these examples so far we have done also, we have used r minus 1's complements to get r's complements. No. I want to get an observation method to get r's complements directly. Instead of using r's complements to get instead of using r minus 1's complements to get r's complements, I want to get r's complements directly. I hope you are understanding my words. I think no one is sleeping in the class, in the virtual class, right? Are you at the systems? Right? Sometimes. Good. Shubham Kumar. Okay, very good. Very frank person. Don't sleep. Yes. Afternoon time, right? Some drowsiness may be there, but I'm there to wake you up, right? Don't switch off the audio. You won't get sleep, right? Right. Once again, I'm addressing the statement which I discussed. What is it here? To get r's complement of a number, we are using r minus 1's complements. Instead of using r minus 1's complements, can't we get r's complements directly? Let us observe whether it is possible or not. If possible, let us get r's complement directly. R's complement directly. So, given number and 10's complements, given number 8's complement, given number 2's complement, given number 16's complements, which are r's complements of respective number system. Right? Given number is decimal and r's complement, which is 10's complement. Given number is octal, 8's complement we need to observe. Given number is binary, observing 2's complement. Given number is hexadecimal, observing 16's complement. Can we find any alternative method to get r's complement directly? Let us see. What is it here? See, in this given, what we are observing, there are 2 zeros in the least significant position. In 10's complement, we have those 2 zeros. Here, before getting first non-zero, point should be understood. Not all the zeros. Before getting first non-zero, if there are any zeros, those zeros as it is here. And here, before getting first non-zero, we have a zero, and that zero is also as it is. In this, we have three zeros before getting first non-zero, those three zeros as it is. Here we have two zeros before getting first non-zero, those two zeros as it is. Tens complements, eights complements, twos complement, 16's complements of respective number systems if we are observing, which are R's complements. What we are observing, if there are any least significant zeros before getting first non-zero least significant digit, those zeros as it is. Before getting first non-zero least significant digit, if there are any zeros, those zeros as it is, those zeros as it is. And next, first non-zero least significant digit. In decimal, we have 8. What is the complement digit we are getting? 2. Here we have 8. First non-zero least significant digit we have is 8. And the complement digit is 2. How to get 2? 10 minus 8, 2. What is 10? Radix R. To get this digit, 10 minus 8 is 2. Is it valid or not? Let us verify. Here, first non-zero least significant digit, 5. Should be subtracted from 8 because R equals 8. 8 minus 5, 3. Yes, satisfied. And here, first non-zero least significant digit. What we have here? 1. Should be subtracted from R. R equals to 2. 2 minus 1, 1. Yes, satisfying. And first non-zero least significant digit. What we have here? 7. Right? What is the radix here? 16. 16 minus 7, 9. Yes, satisfying. That means first non-zero least significant digit should be subtracted from R. R is R. What is R? Radix of the number system. What about remaining? 9 minus 0 is 9. 9 minus 1, 8. 9 minus 2, 7. 9 minus 9, 0. 9 minus 0 is 9. 9 minus 6 is 3. 9 minus 0 is 9. Except first non-zero least significant digit, all the remaining digits, higher order digits, should be subtracted from R minus 1, which is 9. Right? First non-zero least significant digit is subtracted from R. Remaining digits are subtracted from R minus 1. Right? Let us verify. Yes. Coming to octal, 0 as it is. First non-zero is 5, should be subtracted from 8. 8 minus 5 is 3. And remaining should be subtracted from R minus 1, which is 7. 7 minus 0, 7. 7 minus 7, 0. Dinesh Roy, please wait. Let me complete. Let me conclude. Then you can ask the doubts. Please wait. Right. 7 minus 7, 0. 7 minus 0, 7. 7 minus 2, 5. 7 minus 1, 6. 7 minus 0, 7. 7 minus 0, 7. Yes. What is 7 here? R minus 1. Here, 8 minus 5, 3. Remaining, subtracted from 7. Coming to hexadecimal here. 0, 0 as it is. 7 should be subtracted from 16. First non-zero least significant digit should be subtracted from R. What is R here? 16. 16 minus 7, 9. Remaining should be subtracted from R minus 1. How much is that? 15. 15 minus 0, 15 F. 15 minus 2, 13 D. 15 minus 15, 0. 15 minus 9, 6. 15 minus 0, 15 F. 15 minus 12, 3. 15 minus 0, it is F. Coming to binary. There is something special here in binary. Observe this. So in all these three, what we have applied, if there are any least significant zeros before getting first non-zero least significant digit, those zeros as it is, first non-zero least significant digit is subtracted from R, remaining digits are subtracted from R minus 1. Am I using R minus 1's complements here? No. I am writing directly. So to get R minus 1's complement, subtract all from R minus 1. To get R's complements, start from LSD. So before getting first non-zero least significant digit, if there are any zeros, those zeros as it is, first non-zero least significant digit should be subtracted from R. Remaining should be subtracted from R minus 1. Right. Follow correctly with respect to binary. we need to have some more observations. Yes. Here we have 3 zeros, those 3 zeros as it is. First non-zero should be subtracted from R equals to 2. What can be non-zero in binary? What can be non-zero in binary? 1, no other possibility. What can be non-zero in binary? Only 1, 0 or 1. 0 is 0, non-zero can be only 1, should be subtracted from 2. Possibility is only 1, should be subtracted from 2. 2 minus 1, again 1. Why should I subtract? With respect to binary, I am observing one more thing. What is it here? First non-zero least significant bit also as it is. Why should be subtracted from 2? Non-zero digit can be 1. 2 minus 1 is 1 only. Why should I subtract? Directly we can say, so till the first non-zero LSB as it is. Right? Start from LSB. Till the first non-zero LSB as it is. I'm applying same, but I'm observing one more thing with respect to binary 2's complements. Right? Yes. Here up to first non-zero least significant bit as it is, including non-zero as it is. Right? Instead of subtracting, I'm saying directly, because non-zero can be only 1, should be subtracted from R equals to 2. 2 minus 1, again 1. Why? All these. Existing is what? 1. The 1 is the resultant. Let me say that till that bit as it is. Remaining should be subtracted from R minus 1. What is R minus 1 in binary? 1. What is R minus 1 in binary? 1. So, if the bit is 0, 1 minus 0 is 1. If the bit is 1, 1 minus 1 is 0. So, 0 to 1, 1 to 0, 0 to 1, 1 to 0. That means all the remaining bits should be complemented. That's it. Coming to binary once again. Start from LSB until you get first non-zero LSB as it is. Remaining complements. Remaining bits complement. Right. Observe, understand correctly. Right. How to get 2's complement directly? Start from LSB till the first non-zero LSB as it is. Remaining bits complementing. If it is 0, it becomes 1. If it is 1, it becomes 0. Why? It should be subtracted from 1. 1 minus 0 is 1. 1 minus 1 is 0. If the existing is 0, it becomes 1. If the existing is 1, it becomes 0. That's it. Why are you saying that non-zero LSB also as it is? First least significant non-zero should be subtracted from R. So, non-zero digit in binary can be 1, should be subtracted from 2. 2 minus 1, again 1. Why should I subtract? I'm saying. समझ में आ रहा है? और कुछ कंफ्यूजन है क्या? क्या हुआ शुभम? नींद आ रहा था ना शुभम जी? हाँ हाँ. Let me address once again what we have observed in these complements. First, what we used to get these R minus 1's complements, R's complements. So, in this page, what we need to understand, what we need to observe, try to do that. Once again, I'm addressing. Everyone should understand. If you're not giving your presence on my discussion, I cannot help you. Otherwise, give your ROM in your brain, I will install the concept which I know. Hard disk. Send your hard disk, then I'll install all this. So please try to get interest and focus on my discussions. Sure, you will get benefits of these discussions. I'm giving concepts, I'm giving shortcuts, I'm giving my observations, right? So whatever I observed, all that observations I've been mentioning to you, right? So please focus on that instead of giving just take this. I'm not giving like that. So focus on this. So formulas I've given. Then I said we are not using formulas. Then what we are using? Simple things. To get r minus 1's complement, subtracting all the digits from r minus 1. To get r's complements, adding 1 to least significant digit of r minus 1's complement. Am I right? R minus 1's complements, how we are getting? Subtract all the digits from r minus 1. To get r's complement, add 1 to least significant digit of r minus 1. That's what we have used. That is the only thing we have used in these examples. That's it. Then what I mentioned, don't neglect zeros. That is also important thing. And what else I mentioned? Another way for r's complements instead of depending on r minus 1's complements. Right? What we are doing, instead of using r minus 1's complements and adding 1 to least significant digit, what I'm doing? If there are any least significant zeros before getting first non-zero, zeros as it is, first non-zero, subtracting from r, remaining r minus 1. If number is in radix r, how to get r's complement directly? Start from LSD, least significant digit. If there are any zeros before getting first non-zero, those zeros as it is. Subtract first non-zero least significant digit from r, remaining digits from r minus 1. Right? Coming to binary, what we are observing? Start from LSB until we get first non-zero. Right? Those are as it is. 0, 0, 0, 1. 0, 0, 0, 1. And remaining bits, what I mentioned, complement. What is that here? 0 to 1, 1 to 0, 1 to 0, and 1 to 0. Right? Simple thing. Complementing all the bits. Easiest way once you are observing. Shubham, when we have decimal number, we have tens complements and nines complements only. Why do you want to get eights complements of decimal number? We have only two complements. One is a r's, other one is r minus 1's complements. Right? Wait, everything will be cleared. Yes. Wait, everyone. Right? मणिकंडा जी, मुझे भी चाहिए, भेज दो. Yes. After all these, let me give you some more examples for binary. One 101.0100. What is 2's complement of this binary? One's complement, complementing all the bits. Easy. Two's complement. I'm doing the two's complement. 0, 0, 1 as it is. Starting from LSB till the first non-zero LSB as it is. Remaining complementing. 1, 0, 0, 1, 0. That's it. Two's complement. Let me take one more. 0, 1, 1, 0, 0, 0.001. What is two's complement of this? Right? 1 as it is. Because LSB itself is non-zero. Yes, that 1 as it is. There are no least significant zeros before getting 1. So the 1 itself as it is, remaining bits are complemented. That's it. 1, 1, 1, 1, 0, 0, 1. Right? Any questions? What we are doing here, LSB itself is non-zero. So that LSB as it is, remaining bits complementing. If there are zeros, zeros as it is. If there are no zeros, that means LSB itself is non-zero. But LSB is as it is, remaining bits are complemented. If there are zeros, zeros as it is. If there are no zeros, why do we get zeros? First non-zero least significant digit should be subtracted from R, remaining from R minus 1. In this, first non-zero LSB also as it is, remaining bits complementing. Huh? Yeah, no. Yes or no? समझ में आ रहा है? Are you able to understand? If LSB itself is non-zero, how to get? Yes, this is the way we get. Right? 1001.010. What is two's complement of this? 0. Next, 1. Till this same. Because 0, first non-zero as it is. Remaining complementing. What is it? 1, 0, 1, 1, 0. Two's complement. Right? Now, what is two's complement of this? 1 as it is. Complementing all the bits. 1, 0, 1, 1, 0. That's it. Right? What is two's complement of this? 0. Yes. 0. Yes. 0. Now, 1 also as it is. Because till the first non-zero LSB as it is. What about remaining bits? No more bits to complement. This is a two's complement of given number. See, start from LSB. 0 as it is. 0 as it is. 0 as it is. First non-zero as it is. Remaining bits complementing. But no more bits to complement. No more bits to complement. Two's complement of a binary number is resulting same number. I hope you are understanding. Sneha. Right. Rata Priya. Wait. Right. So 1, 0, 0, 0. What is it here? 1, 0, 0, 0. Whose complement is what? 0 as it is, 0 as it is, 0 as it is, 1 also as it is. First non-zero LSB. Remaining bits should be complemented. No more bits to complement. So, whose complement of a binary number is resulting same number? If it is 1, 0, 0, 0, 0, 0, then also 0, 0, 0, 0, 0 and 1. Right? Yes. If you have a 1, you can write any number of zeros whose complement is same. Whose complement is same. Any other possibility for getting two's complement is same in binary? All zeros. Already we discussed this while giving formulas itself. I mentioned that if it is all zeros, two's complement R, R's complement itself is all zeros. Right? If the given number is all zeros, r's complement is again all zeros. One possibility is all zeros, whose complement is same number. Other possibility is 1. You can write any number of zeros. MSB is 1. Remaining bits are zeros. Then all the whose complements will be same. What is it here? MSB is 1. Remaining bits are zeros. You can have any number of zeros. Doesn't matter. Whose complement will be same number. One possibility is all zeros, whose complement is same. Second possibility is 1 all zeros. Shravan Kumar. Wait. Two possibilities for getting whose complement is same. One is all zeros. Second one is 1 all zeros. MSB is 1. Remaining bits are zeros. Then whose complement is same number. So now I've seen some questions in the messages, sir. I hope I have cleared all those doubts, sir. Right. Raja T. Raja T. In octal or hexadecimal or decimal, if LSG itself is non-zero, subtract that from R, remaining from R minus 1. Logic is same. If there are zeros, we are using zeros. If there are no zeros, LSD itself is non-zero. That LSD should be subtracted from R, remaining from R minus 1. That's it. Raja T. Understanding? Mr. Raja. Yes. Navin. Yes. If you are comfortable, you can use that. Not a problem. Yes. So finally, what we have observed, getting two's complement directly. If a given number is in binary, I'm writing two's complement directly. Navin, please down the hand. You are raising the hand, please. Right? Wait, I'll give you time. Right? If you have doubts, right? Now, at the end, what we have observed, two's complement of a binary number is becoming same number. When is it possible? 1 all zeros. 1 all zeros. Other possibility is all zeros. All zeros two's complement is again all zeros. If it is 1 all zeros also, two's complement is same. If you have understood this, I would like to frame a question and try to answer yourself, right? Try to answer this previous question. Shweta Sharma. Wait. Let me elaborate the question. I want to give you some more information. Understand the question correctly. Chandu Srinivasa Manikanta Surya Namburi. What is the meaning of that statement? I cannot pronounce your entire name. When I see your name, let me say that multi-name. Right. Yeah, I'll clear all the doubts. Wait till the end. You can hold me whatever the time you require. Multi-name. Yes. Most of you have answered correctly. Right. Listen. Read the question. 2's complement of a non-zero binary integer with minimum 3 bits is itself when except dash. Right? Let me repeat the statement once again. 2's complement of a non-zero binary integer with minimum 3 bits is itself when except dash. Let us see one by one option. Let me use. Already we know when do we get 2's complement is same? 1 all zeros. All zeros or 1 all zeros. All zeros is excluded. Why? In the question itself it is mentioned non-zero binary integer. What do you mean by this? All zeros is excluded. Right? As it is mentioned, non-zero binary integer. If it is all zeros, 0. Non-zero binary means there must be at least one bit is 1, non-zero number. Right? Don't think that all the bits must be non-zero. No, no. The value should be a non-zero. Value is 0 means all zeros. A non-zero binary integer. That is the reason all zeros is excluded. Next possibility is what? 1 all zeros. MSB is 1, remaining bits are zeros. Which one is correct with respect to that answer from the given statement? Let us understand. Binary integer with minimum 3 bits is itself when except dash. If I say first option, except MSBR1, except MSBR1, except MSBR1. What do you mean by this? MSB is not 1, except MSBR1. MSB is not a 1. MSB is not a 1 means MSB is 0. Remaining bits are 1s. Point should be understood correctly. Except MSB are 1. MSB is not 1. MSB is not 1 is indicating MSB is 0 because it is binary. MSB is 0. Remaining bits are 1s. Except MSB are 1. So all the bits are 1s except MSB. MSB is not 1. MSB is not 1 means MSB is 0. Do we get 2's complement of this is same? No. Why? 1, 0, 0, 1 is 2's complement of this. No. It is wrong. Right? Then when except LSBR1, option B I am verifying. Except LSBR1. LSB is not 1. LSB is not 1 means LSB is 0. Remaining bits are 1s. Except LSBR1. That means LSB is not 1, LSB is 0. Remaining bits are 1s. What is 2's complement of this? 0, 1, 0, 0. I'm starting with LSB. 0, 1, 0, 0. Till this it is same, remaining are complement. 0, 1, same. Then remaining bits complement 0, 0. Is it getting same? No. Again it is wrong. Then except LSBR 0. What is here? Except LSBR 0. LSB is not 0. LSB is not 0 means LSB is 1. Remaining bits are zeros. इसका 2's complement क्या है? 1, 1, 1, 1. That means all ones. Is it getting same? No. So C also no. D must be correct. नहीं तो question गलत हो जाएगा. Question becomes wrong. D must be correct. When you are confirming that A, B, C are wrong, D must be correct. Otherwise, question is wrong. Except MSB are 0. That means MSB is not 0. MSB is 1. Remaining bits are zeros. 2's complement of this is same. 1 all zeros. 2's complement is what? 1 all zeros. Any questions? Any doubts? Yes. We know the answer. We are verifying with the option. Option D is correct. We know the answer. The only thing is, I have observed most of you are right. Some of you have answered either A, B. I can see what you have done. I can understand what mistake you have done. Please check it. You might not have observed except word. Right? So there is a reason MSB are 1. People thinking that MSB is 1. No. Except MSB are 1. That means MSB is not 1. MSB is 0. Remaining bits are 1s. Right? So correctly, except MSB are 0. MSB is not 0. MSB is not 0 means MSB is 1. Remaining bits are zeros. Yes, that's what we are searching for. With this question, I would like to give you one more caution about competitive exams. Don't be in a hurry. Each and every word has a meaning. They are checking our observation skills, whether we are observing given correctly or not. Sometimes they are giving extra data. So you may be using a formula depending on concept. In that formula, it may not be required to use one parameter. Unknowingly, they might have mentioned that parameter. So because of that parameter, you may be deviating to use another formula. This is what is happening in competitive exams. Be clear about all these if you're expecting a result. Right? Observe each and every word correctly. We know the answer for this question, but some of you have answered wrongly. The reason is you are not observing what is given correctly. Right? I think you are understanding now in right way. then you might be understanding what is the difference from semester exams or college exams and competitive exams. Please understand these words in a right way, positively. We are there to help you with our experience. A quality will be given. Sure, if you are utilizing, there will be better results. Right? So we know the concept, but how we are applying that concept is giving result. So in the 3 hours, we need to understand the given, and you need to apply the concepts you have learned in right way to get better results. Otherwise, what we say after coming out of exam hall, simple mistakes. Otherwise, I would have been in top 10 or top 100 or whatever you say, general words. Every student have been observing silly mistakes I have done. Otherwise, I would have been in top 10 or top 100. People have been saying this. Why are you doing that mistakes? That's what you need to learn now before going to final exam. That's what I suggest you. You should not do mistakes. Being my student, if you are understanding my words in a right way, positively, I hope you won't do such mistakes in any subject, not only this subject, with respect to all the subjects I have been mentioning. Right? So, be positive, right? Be clear in the concepts, and give your presence while reading, question, then apply. Each and every word you need to observe correctly. In this, except has been confusing us. Am I right? Right. I would like to address one more important thing. Why with minimum 3 bits? Why can't it be 2 bits? 2 bits, 1 0, 2's complement is 1 0. Is there any problem with that? No, it is also correct. 1 0, 2's complement is 1 0. Why it is mentioned with minimum 3 bits? Is there any reason for that? Yes, there is a reason. What is that? With 1 0, 2's complement is 1 0. But if 1 0, if you are observing, except MSB, remaining bits are zeros. Except LSB, remaining bits are ones. Except MSB, 0. Except LSB, 1. That means with respect to bits, 2 options are correct. With respect to 2 bits, 2 options are correct. From 3 bits onwards, 1 0 0. Only one option. What is that here? Except MSB 0. 1 0 0 0. Except MSB 0. 1 0 0 0 0. You can write any number of zeros. Except MSB, remaining are zeros. But when we are coming to 2 bits, 1 0, except MSB 0 or except LSB 1. That means 2 options are correct with respect to 2 bits. To exclude that ambiguity, right? It is mentioned with minimum 3 bits. It was the previous question. Hats off to the examiner for observing all these to frame a question. That too, mostly trying to bluff the students. Right. So finally, what is that here? Answer is except MSB are 0. Right. With 2 bits, 2 options will be correct. 3 bits and above, only one option is correct. Right? मजा आ रहा है? If you are willing to learn, you feel enjoy, right? Uh, it is minimum 3 bits, not compulsory 3 bits. Who is that? I'm not able to see. Someone is asking that when it is 3 bits, why you have used 4 bits? It is minimum 3 bits. Bharat, if I speed up, I can see thousands of messages. Right? It's not only for few, it is for everyone. Please. Right? Why are you raising your hands? Bhaskar, Yashwant, I'll give you chance at the end. Please wait. Ha. I hope no one is having any questions, sir. If you have any questions, I'll discuss later. Let me repeat about this question once again. One more. Who is that? Right? Even though you are raising your hand, I won't give you chance now. Please wait. So let us understand the question once again. What way we need to understand the given question, right? 2's complement of a non-zero binary integer with minimum 3 bits is itself when except dash. I need to fill the dash with the given option, sir. Which one is giving correct answer? That one you have to choose. Because we know the answer. 2's complement of a binary number is resulting same number when all zeros is there, 2's complement is same. The other possibility is 1 all zeros. MSB is 1, remaining bits are zeros. Then also we are getting 2's complement is same. So here non-zero means all zeros is excluded. Second possibility is 1 all zeros. So this 1 all zeros comes under which option we have to choose. So for that except dash, except MSBR1, except MSBR1, MSB is not 1. So MSB is 0, remaining bits are 1s. If I say option B, except LSBR1, LSB is not 1 means LSB is 0, remaining bits are 1s. And option C is except LSB are 0, LSB is not 0, LSB is 1, remaining bits are zeros. Except MSB are zeros. What do you mean by this? MSB is not a 0, MSB is 1, remaining bits are zeros. So except MSB are 0 is giving correct answer. Why it is mentioned 3 bits minimum also we have tried to understood. What is it here? We have tried to understand what is it here. With 2 bits, if you are considering 1 0, except MSB 0, except LSB 1. These two are correct, right? Except MSB 0, except LSB 1. Those two will be correct. There is a reason the correct option is D, right? Right? Now, Right, let me take one or two examples to get complements, to get R's complements directly. Find 8's complements of octal number. Find 16's complements of hexadecimal number. Directly we want to write complements. Find 10's complement of a decimal number directly. Find 10's complement of decimal number. Last one also. I'm expecting you to write R's complements directly. Here we want to write 8's complement. Then what is it here? 0, 0, 8 minus 3, 5. Right? Remaining should be subtracted from R minus 1. What is that here? 7. 7 minus 0, 7. 7 minus 1, 6. 7 minus 7, 0. 7 minus 1, 6. 7 minus 0, 7. 7 minus 2 is 5. 7 minus 0 is 7. What is this here? 8's complement of given octal number. What we want to get here? 16's complements of hexadecimal number. What should I do? 0, 0, 0, 16 minus 8, because first non-zero least significant should be subtracted from 16. 16 minus 8, what we get here? 8. Remaining should be subtracted from 15. 15 minus 0 is 15, F. 15 minus 1, E, 14. 15 minus 2, 13, which is D. And 15 minus 9, 6. 15 minus 10, which is 5. 15 minus 0, F. And here it is again, what is it here? 10's complement. How to get that? 0, 0, 0, 10 minus 2, 8. Remaining should be subtracted from 9. 9 minus 5, 4. 9 minus 0, 9. 9 minus 1, 8. 9 minus 7, 2. 9 minus 9, 0. 9 minus 0 is 9. 9 minus 2 is 7. That is a 10's complement. Here again, 10's complements which I asked. Decimal number. So 10 minus 7, 3. Least significant itself is non-zero. Then remaining should be subtracted from 9. 9 minus 0 is 9. 9 minus 0 is 9. 9 minus 2 is 7. 9 minus 9 is 0. 9 minus 0 is 9. 9 minus 1 is 8. I hope now all the doubts are cleared, because some of you are asking, right? For them, I have taken these examples also, not only for binary, for the remaining also. Pavan Kumar, right? So for octal number, 8 and 8 minus 1's complements. For base 7, 7's complements and 7 minus 1's complements. R and R minus 1. Gummuluri Pavan Kumar. For octal number, 8's complements, 8 minus 1's complements. For base 7, 7's complements, 7 minus 1's complements. Right? Yes. Yeah, Harsha, I'll try. But let me follow my way because people have to tune to me the way I'm discussing my words. Right? What is it here? Tuning is required. Let me do that. Obviously, your expected speed will be there soon. Then you may be saying again, slow down, right? Don't, right? Think of all these. I'll take care of that speed and all because you are thinking about one person or alone, but I have to think about everyone, and I've been observing many batches, how people have been understanding and what speed is accurate. So that is the reason I've been maintaining this. Please, right, bear with me. Yeah, that's what I've been saying. People have been saying that. Right? I hope it is fine. Let me follow this to get benefits by everyone. Right? I'll speed up whenever it is required. When I observed everyone is tuned to me, it is synchronized with my frequency of catching, then I'll speed up. Until that, I have to maintain this. So please bear with me. And we'll be getting into most important topic from number systems, which is a signed number representation pattern. Important one for competitive exams, and sometimes in ESC we have been getting two questions. Right? So only from this area, mostly we have been getting, right, two questions only from the signed number representation binary. So before getting into that, let me take a small break. We'll continue after 15 minutes break from now, right? Welcome back. The next topic is signed number representation in binary. What do you mean by this, sir? When we have both positive as well as negative numbers. Till now, we haven't considered a negative number is there. Assuming that only positive numbers are there existing, there is unsigned numbers. Whatever we have discussed till now is unsigned numbers or unsigned binary numbers we have discussed. Now, if there is a possibility for both positive as well as negative number, what can we do? When we have both a positive as well as negative number, what can we do? So, to differentiate positive and negative numbers, we are using plus and minus symbols. To differentiate positive and negative numbers, we have plus and minus symbols. When we have both positive and negative numbers, we are understanding with plus and minus symbols, positive and negative numbers. But digital system cannot understand plus and minus symbols because systems can accept only ones and zeros. Using ones and zeros only with predefined protocols, you need to feed the information when we have signed numbers, which is positive as well as negative numbers. When we have both positive as well as negative numbers, using ones and zeros only with predefined set of rules, how we are representing signed numbers. So other than ones and zeros are not accepted. Using ones and zeros only, there must be rules. What are the rules? What are the representations we have? Let us understand. So what is it here? Using ones and zeros only with predefined protocols, how we are differentiating positive and negative numbers. That's what we are trying to understand. So for that, we have total 3 representations. One is one's complement representation. Third one is two's complement representation. Signed magnitude, one's complement and two's complement representation. We have total 3 representations. Let us see one by one. What is it here? First thing, when we have both positive and negative numbers, I cannot use plus and minus symbols because digital system cannot understand plus and minus signals. So it has to be fed the information with ones and zeros only. How we are feeding that information using ones and zeros only? Let us see. Now, first one is signed magnitude. Signed magnitude representation. What are the rules behind this representation? Let us try to understand. What are the rules here? Sign plus magnitude. Sign plus magnitude. Signed magnitude means sign plus magnitude. What is this here? MSB is explicitly for sign and remaining n minus 1 bits are used for magnitude. When I'm using n bits for representing signed number, MSB is only for sign. Remaining n minus 1 bits are used for magnitude with the binary weights or true binary weights, whatever we are using, the same weights we are using for representing magnitude. MSB is exclusively for sign. If MSB is 0, number is positive. If MSB is 1, number is negative. If MSB is 0, number is positive. If MSB is 1, number is negative. Try to understand rules behind this. What is it here? MSB is explicitly for sign, which is not having any weight. The remaining n minus 1 bits. Why I'm saying that n minus 1 bits? Assuming I'm using n bits. So remaining n minus 1 bits are used for magnitude. If MSB is 0, number is positive. If MSB is 1, number is negative. Right. What about magnitude? With n minus 1 bits, I'm representing magnitude with true binary weights. If I say it is like this, 1, 0, 1, 0. What can be the value? The representation is in signed magnitude. The bits I'm using 4 bits and the representation is 1, 0, 1, 0. What can be the decimal equivalent of this? If MSB is 1, minus 0, 1, 0 magnitude is what? 2. So it is now minus 2. Hope you are understanding. 1, 0, 1, 0. Right? So 1 MSB is indicating negative. 0, 1, 0 magnitude is what? 2. 2 power 0, 2 power 1, 2 power 2 weights if I am using to calculate magnitude with 0, 1, 0, it is giving 2 and MSB is 1 minus. Next, 1, 1, 0, 0. What can be the decimal equivalent? MSB is 1 negative, 1, 0, 0, it is 4. Now, 1, 1, 1, 0. What can be the value? MSB is 1 minus 1, 1, 0 is 6. 1, 1, 1, 1. MSB is 1 negative, 1, 1, 1 is 7. It is minus 7. 1, 0, 0, 0. What can be that? 0, 0, 0 magnitude is what? 0. As MSB is 1, we can say it is minus. If it is 0, 0, 0, 0, magnitude is 0, right? MSB 0 is indicating positive. Next, 0, 0, 0, 1. What we get here? MSB is 0, positive. 0, 0, 1, it is 1 plus 1. 0, 1, 0, 0. What is decimal equivalent? MSB is 0, positive. 1, 0, 0 is 4. 0, 1, 0, 1. What we get here? MSB is 0, positive. 1, 0, 1 is 5. 1, 1, 1 if I consider, sorry, 0, 1, 1 if I consider, what is it here? MSB is 0, positive. 1, 1, 1, it is a 7. I'm not considering all the 16 combinations. I'm using 4-bit representations to understand how it is represented. So here, if you're observing, MSB is 1, number is negative. MSB is 0, number is positive. And with that protocols, if you're representing the most negative number we are observing is minus 7, most positive number is plus 7 using 4 bits. And also, one more important thing, 0 is having 2 representations. One is 1 all zeros, second one is 0 all zeros. Right? We are getting 2 representations for 0. Right? That is drawback of this representation. Do we have a plus 0 minus 0? Do we have plus 0 minus 0? No. We have only 0. But this representation is saying that we have a plus 0 and minus 0. There is drawback of this representation. You may use any number of bits. With that bits, it is showing that there are plus 0 minus 0, 2 representations. Right? Which is wrong. Which is a drawback of this representation. Then what is it here? If you are observing, the rules first, try to understand. MSB is 0, number is positive. MSB is 1, number is negative. And what about magnitude? I'm using n minus 1 bits for magnitude. Using n minus 1 bits with binary weights, we are calculating magnitude. The same thing we are using with examples here. MSB is 1 negative, 0, 1, 0 is 2. So MSB is 1, 100 is magnitude, 100 is 4, MSB is 1 minus. So 1, 110. So MSB is 1 negative, 110 is 6. MSB is 1 negative, 111 is 7. And MSB is 1 negative, 0000 is 0. MSB is 0 positive, 000 is 0. MSB is 0, then positive, 001 it is 1. MSB is 0 positive, 100 is 4. MSB is 0 positive, 101 is 5. MSB is 0 positive and 111 is it is 7. So I'm using the protocols which are mentioned. With the protocols, we are observing a problem. What is the problem here? 0 is having two representations. One representation is saying that plus 0, other one is saying that minus 0. And also, if you are observing the range using 4 bits, most negative number is what? Minus 7. The most positive number, plus 7. Am I right? Most negative number is minus 7. Most positive number is plus 7. Using 4 bits. Similarly, let me write that same. 2 power 4 minus 1 minus 1. Why? 2 power 4 minus 1 is what? 2 power 3. 2 power 3 is 8. 8 minus 1 is 7. Minus 7. 2 plus 2 power 4 minus 1 minus 1. Then 4 is what? Number of bits I am using. If I use n bits, minus of 2 power n minus 1 minus 1 to plus 2 power n minus 1 minus 1. What is this? Range of n bits in signed magnitude representation. In signed magnitude representation, what is here? Range of n bits is a minus of 2 power n minus 1 minus 1 to plus 2 power n minus 1 minus 1. Also, what else we can say? It is having plus 0 is all zeros, minus 0 is 1 all zeros. It is not only 4 bits. If I use 5 bits, 5 zeros is plus 0, 1 4 zeros is minus 0. That's what drawback we have observed in signed magnitude representation. Once again, let me address each and every point I discussed with respect to signed magnitude. Signed magnitude is nothing but sign plus magnitude. MSB is for sign, remaining bits for magnitude. MSB is 0, number is positive. MSB is 1, number is negative. That is the protocols behind this representation. With that protocols, if you are proceeding to write numbers, there we are observing, we are getting two zeros. One is plus 0, other one is minus 0. And also, the range is, if you are observing 4 bits, minus 7 to plus 7. If I am fixing with n bits, the formula we are getting that minus of 2 power n minus 1 minus 1 to plus 2 power n minus 1 minus 1. That is about signed magnitude representation. One's complement representation. One's complement representation. Why it is named as one's complement representation, we understand. First of all, let us understand rules behind this representation. One's complement representation. Right? In this, MSB is also having weight, MSB only having negative weight. Point should be understood correctly. In this representation, MSB is also having weight, MSB only having negative weight. Right? MSB only having negative weight. What is weight here? Minus of 2 power n minus 1 minus 1 when I'm using n bits. MSB only having negative weight. And the remaining bits are having positive weights. Right. Let me repeat once again the rules. In this representation, I'll give you clarity. Try to follow my discussion. I'll give you clarity about each and every doubt you have now. Step by step, I'm going to clear your doubts. Right? So follow correctly. in this ones complement representation, MSB only having negative weight. The weight is minus of 2 power n minus 1 minus 1. And all the remaining bits are having positive weights. The weights also we have mentioned 2 power n minus 2 power n minus so and so 2 power 1 2 power 0. These are rules for representing signed numbers in ones complement representation. If I use 4 bits, for example, if I use 4 bits B3, B2, B1, B0. B3, B2, B1, B0. If I use 4 bits, can you help me? What can be the weights for bits from MSB to LSB? What is the weight for MSB now? Minus of 2 power n is 4 minus 1 minus 1. How much is that? Minus of 2 power 4 minus 1, 2 power 3, 8. 8 minus 1 is 7, minus 7. Right? So weight of MSB is minus 7. What about next bit? 2 power n minus 2, 2 power 4 minus 2, 2 power 2. It is plus 4. Next plus 2. Next plus 1. Check it. 2 power 1, 2 power 0. Right? Now, if I consider examples like this, 1 0 0 0, what can be the decimal equivalent of this? 1 0 0 0, what can be the decimal equivalent? 1 into minus 7. Always decimal equivalent is summation of weighted values. With different rules, it may be used different weights. When we are using different set of rules, we may be getting different rules. But always decimal equivalent is summation of weighted values. Digit weight multiplying weighted values, take summation of weighted values. To get decimal equivalent, always use summation of weighted values. Summation of weighted values. Sai. Banawat Sai. I need to use 5 bits to represent 12. There is a limitation with 4 bits. I can represent minus 7 to plus 7, which was about, I think, signed magnitude. You might have asked a question. There, how to represent 12, you are asking. For that, I'm giving clarity. For representing 12, 4 bits is not sufficient. We should go with the higher number of bits. So, always 4 bits, no. I did not say that. I am trying to understand concept with 4 bits. As I'm comfortable with 4 bits, I'm using 4 bits. Instead of using very less number of bits, instead of using more number of bits, I'm using 4 bits to cover the concepts. So don't think that signed numbers means only with the 4 bits. No. Right? Not required 8 bits also. Usha. It is not 8 bits. With 5 bits, the range will be minus 15 to plus 15. The 12 he mentioned will be in this range. The minimum number of bits. You can represent using 8 bits. The minimum number of bits is 5 for representing 12. Maybe plus 12 or minus 12. For representing 12, 5 bits is sufficient. Right? Usha. Right? Okay. I'll give you all that clarity. Right? Let me cover what I would like to cover. Right? Always decimal equivalent is what? Summation of weighted values. Summation of weighted values. So, calculate this. 1 into minus 7 plus 0 into 4 plus 0 into 2 plus 0 into 1. Finally, what is the value? I'm getting minus 7. What is it here? Minus 7. What is it here? Once again, what is it here? 1 into minus 7 plus 0 into 4 plus 0 into 2 plus 0 into 1. Final resultant is what? Minus 7. Now, 1001 if I consider, what is the decimal equivalent? 1 into minus 7 plus 0 plus 0 plus 1 into 1. So, minus 7 plus 1, what is the value? Minus 6. 1100. Help me. Minus 7 plus 4 plus 0 plus 0. It is minus 3. 1110. Minus 7 plus 4 plus 2 plus 0. What is the value we are getting? Minus 1. 1111. What is the decimal equivalent? Minus 7 plus 4 plus 2 plus 1. It is 0. I hope everyone is able to calculate this. Simple thing is summation of weighted values. You are using different weights. The only thing is different weights we are using. Decimal equivalent is always summation of weighted values. Digit into weight and add all those. Weighted values should be taken summation, right? 1, 1, 1, 1. What we get here? Minus 7 plus 4 plus 2 plus 1. 0. 0, 0, 0, 0. Whatever will be the weights, weighted values are 0, sir. Summation of weighted values will be 0. No doubt in that. 0, 0, 0, 1. Decimal equivalent is what? 0 plus 0 plus 0 plus 1 into plus 1 plus 1. 0, 1, 0, 0. Decimal equivalent is what? Plus 4. 0, 1, 1, 0. Decimal equivalent is what? Plus 6. 0, 1, 1, 1. Decimal equivalent is what? Plus 7. If you are clearly observing, in this, MSB is 1, number is negative. MSB is 0, number is positive. Correct? In this also, MSB is 1, number is negative. MSB is 0, number is positive. With that protocol, once again, if you are differentiating these two, one is minus 0, other one is plus 0. One is minus 0, other one is plus 0. Right? In this MSB is 1, in this MSB is 0. Negative, positive. So, once again, we are getting same problem in one's complement representation. Even though we are going with weights, instead of using exclusively for sign MSB, even though I'm using some weights, so with this representation, I'm getting again two zeros. One is plus 0, other one is minus 0. Right? So, the range also, if you are observing, what is it here? Minus 7 to plus 7. If I'm using n bits, again, what we get? Minus of 2 power n minus 1 minus 1 to plus 2 power n minus 1 minus 1 using n bits. Again, we are getting same drawback. Plus 0 is all zeros. Minus 0 is all ones. No need to worry. All these slides will be uploaded. Yesterday itself I have sent the slides. It may be uploaded, and every slide will be uploaded. No need to worry about these notes. Right? Understand correctly? I already told you why it is called one's complement. I'm going to address. Just hold on. I told you already. You will be getting the doubts. Just to follow my discussions. I'll give you clarity about each and every doubt you are getting now. Fine? Please. Right. Follow what I've been discussing. Why these are called, I'll discuss later. Now, with this weighted protocols in one's complement representation, if you're observing, once again, the same problem is there, which is a 0 representation. 0 is having two representation. One is plus 0, other one is minus 0. In this representation also, MSB is 1, number is negative. MSB is 0, number is positive. Every slide will be uploaded. No need to worry. Right. Now, third representation is 2's complement representation. 2's complement representation. In this, what is it? MSB is also having weight. MSB only having negative weight. Weight is different from 1's complement representation. Minus 2 power n minus 1. And all the remaining bits are having positive weights. 2 power n minus 2, 2 power n minus 3, so and so, 2 power 1, 2 power 0. Right? So what is it here? MSB is having negative weight and weight is minus 2 power n minus 1 and all the remaining bits are having positive weights. Right? Now, if I use 4 bits, B3, B2, B1, B0. Can you help me the weights of respective bits? What can be the weight of MSB? Minus 2 power, number of bits is 4, 4 minus 1. That means minus 2 power 3, it is minus 8. Next, plus 4. Next, plus 2. Next, plus 1. Minus 8 plus 4 plus 2 plus 1. Then 1, 0, 0, 0. If I use, what can be the decimal equivalent? 1 into minus 8 plus 0 plus 0 plus 0. It is a minus 8. 1, 0, 0, 1. What can be the decimal equivalent? Minus 8 plus 0 plus 0 plus 1. It is minus 7. 1, 1, 0, 0. What can be the decimal equivalent? Minus 8 plus 4. It is minus 4. 1, 1, 1, 0. What can be the decimal equivalent? Minus 8 plus 4 plus 2. It is minus 6. 1, 1, 1, 1. Decimal equivalent is what? Minus 8 plus 4 plus 2 plus 1. It is minus 1. 0, 0, 0, 0. What we get here? 0. 0, 0, 0, 1. What we get here? 0, 0, 0 plus 1. It is plus 1. 0, 1, 0, 0 plus 4. Because 0 plus 4 plus 0 plus 0. It is plus 4. 0, 1, 0, 1. It is a plus 5. 0, 1, 1, 1. It is a plus 7. Right? I hope everyone is following how I'm writing equivalents. Simple thing is summation of weighted values. From where we are getting these weights? From these rules. Using these rules, I am writing weights. To calculate decimal equivalent, I am using summation of weighted values. Right? Digit, weight, and addition of all these. Summation of weighted values. Right? Now, in this also, MSB is 1, number is negative. MSB is 0, number is positive. In this representation also, MSB is 0, number is positive. MSB is 1, number is negative. And also, we are getting only one representation for 0. We are getting only one representation for 0. Shilpa. Sajjan Singh. Sorry. Yes. Yeah. Yeah. Yes. 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 Unknowingly I did a mistake. Right. Minus 8 plus 4 plus 2 is minus 2. Correct. Thank you. Yes. 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 Thank you. Thank you. Thank you. Yes. 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 Right. So in this, if you are observing, MSB is 1, negative. MSB 0, positive. And also, what else we are observing? 0 is having only one representation. 0 is having only one representation. And if you are observing the range, what is the range? Minus 8 to plus 7 using 4 bits. Minus 2 power 4 minus 1 to plus 2 power 4 minus 1 minus 1. Right? Minus of 2 power n minus 1 to plus 2 power n minus 1 minus 1. That is the range of n bits. Using n bits in 2's complement representation, the range is minus 2 power n minus 1 to plus 2 power n minus 1. And also 0 is having only one representation. 0 is having only one representation. Try to follow the rules once again. In 2's complement representation also, MSB is having negative weight. MSB only having negative weight, and all the remaining bits are having positive weights. And all the remaining bits are having positive weights. With that rules, what are the weights we have mentioned? If I go with 4 bits, MSB is having weight is minus 8. Next, plus 4, plus 2, plus 1. With these weights, if I consider some of the examples using 4 bits, I have observed the most negative number, most positive number, and 0 representation. All these we have observed. And in this, if you are observing, MSB is 1, number is negative. MSB is 0, number is positive. Number is positive. And also, 0 is having only one representation. The range, if you are observing, using 4 bits, it is minus 8 to plus 7. If it is used n bits, minus 2 power n minus 1 to plus 2 power n minus 1 minus 1. Right. Right. Sign the magnitude. Once again, I'm covering. Follow that correctly. Rules of 3 representations. Sign to magnitude, sign plus magnitude. The rule is what? MSB is not having weight. MSB is considered explicitly for sign. And all the remaining bits are used for magnitude. MSB is 0, number is positive. MSB is 1, number is negative. And in this, if you are observing, right, the range is minus of 2 power n minus 1 minus 1 to plus 2 power n minus 1 minus 1. And the drawback is 0 is getting 2 representation. One is plus 0, other one is minus 0. Other one is minus 0. That is a signed magnitude representation. Sign plus magnitude. MSB is only for sign, which is not having any weight. N minus 1 bits are used for magnitude with the binary weights. And drawback is 0 is getting 2 representations. One is saying that plus 0, other one is saying that minus 0. Coming to 1's complement representation. Why these are called 1's complement representation? I'll give you clarity. Until that, hold on. So at this moment, let us follow the rules. So in this 1's complement representation, MSB is also having weight. MSB only having negative weight. In this representation, MSB is also having weight. MSB only having negative weight. And all the remaining bits are having positive weights. And the weights already represented. What is it here? Minus of 2 power n minus 1 minus 1, 2 power n minus 2, so and so 2 power 1, 2 power 0. With these rules, if I go with 4 bits, weight of MSB is minus 7, next plus 4, plus 2, plus 1, using 4 bits. And don't think that always we need to use 4 bits only. I'm trying to convey the concept with 4 bits. Please understand in a right way. Right? Don't assume always it must be 4 bits only. It can be 5 bits, it can be 10 bits, it can be 100 bits. Doesn't matter. Concepts will be same. I'm explaining, I'm trying to convey the concepts with 4 bits. Right? So if I'm using 4 bits, MSB weight is minus 7. Next bits are plus 4, plus 2, plus 1 weights. With that weights, if I calculate decimal equivalents of representations using summation of weighted values. using summation of weighted values. Right? Always decimal equivalent is summation of weighted values. You may be using your own protocols, your own rules. Always decimal equivalent is summation of weighted values. Now, to calculate decimal equivalent, what we're doing here? 1 into -7 plus 0 plus 0 plus 0. First representation I'm saying. That will be -7. And similarly, if you're calculating decimal equivalent, whatever we have done, you can see. And in this also, again, we are getting two representations for 0. One is saying +0, other one is -0. In this also, MSB is 1, number is negative, MSB is 0, number is positive. And the range is also -7 to +7. And n bit is minus of 2 power n minus 1 minus 1 2 plus 2 power n minus 1 minus 1. And in this also, again, we are getting two representations. One is +0, all zeros, -0 is all ones. That is a ones complement representation. In this, MSB is also having weight, MSB only having negative weight. And all the remaining bits are used with positive weights. And that is a ones complement representation. Right. Coming to two's complement representation. In this, almost similar rules like ones complement. Right? But MSB weight is different. In this also, MSB is having weight, MSB only having negative weight, and the weight is -2 power n minus 1. And all the remaining bits are having positive weights, 2 power n minus 2 power n minus so and so, 2 power 1, 2 power 0. Right? Now, if I go with 4 bits, the weights already I have discussed, I have mentioned, it is MSB weight is negative, -8, next +4, +2, +1. With these weights, again, I'm going with examples. I'm calculating decimal equivalents using summation of weighted values. Then again, we are observing here, what is here? MSB is 1, number is negative, MSB is 0, number is positive. And 0 is getting only one representation. There is advantage here. And range is -8 to +7 means using n bits, it becomes -2 power n minus 1 2 plus 2 power n minus 1 minus 1. -2 power n minus 1 2 plus 2 power n minus 1 minus 1. Here we are getting only one representation for these are rules. Do you have any doubts in the rules except why these are called ones complement, two's complement? Triveni, wait. Sahil Singh, wait. While designing the system, one combination for each and every number. When we have two combinations for one number, system is in a confusion. It should not have two representations for one number. If you have +0 -0, yes, we can have. But we don't have +0 -0. While analyzing that arithmetic analysis, right, are we considering sometimes +0 -0? No. both values are same, that is treated by you, but system also has to treat that, right? You may be using one representation, I may be using another representation. System is not in a position to respond. There will be ambiguity, there will be a problem. That should not be there. Shubham. Shubham. Right. Yes, sir. Gopal Krishna. Sanam Pudi. Yes. Only thing is, one is not having weight, other one is not, I don't know, other one is having weight. Yes. I will discuss, sir, with respect to your doubts. Some are rising hands, sir. I'll discuss. Right. Okay. I'm using some protocols or rules, sir, for representing one's complement, two's complement, as well as signed magnitude. Each and every representation rules we have discussed, right? All those are understood, right? Yes. Okay. Before proceeding to this, right, there are some similarities among three representations. Follow correctly. I'm flipping the slides frames. Signed magnitude, one's complement, and two's complement representation. Once again, what is here? Signed magnitude, one's complement, and two's complement representation. There are similarities among three representations. What can be that similarities? Right. What are that is MSB 0 positive, MSB 1 negative. The first thing is MSB 0 positive, MSB is 1 negative number. MSB is 0, then number is positive. If MSB is 1, right, negative, that is the first one. That is similarity. Any other similarity among three representations? Positive numbers representation is same. Positive numbers representation is same. If you are having a positive number, for example, plus 4 is there. Plus 4 is 0, 1, 0, 0 in signed magnitude, one's complement and two's complement representation. For positive numbers, signed magnitude, one's complement and two's complement representations are same. Observe correctly. For positive numbers, the representations are same. First similarity, once again, MSB is 0, number is positive. MSB is 1, number is negative. If MSB is 0, number is positive. If MSB is 1, number is negative. Second similarity is what is it? All the positive numbers representation is same. Not only upper range. Some people are saying that plus 7 is common in all three representations. That is upper limit is common. Not only upper limit. What is that here? All the positive numbers representation is same. In signed magnitude, one's complement and two's complement representation. Let me repeat similarities once again. If MSB is 0, number is positive. If MSB is 1, number is negative. That is the first thing. Second one is positive numbers representation is same. For positive numbers, all signed magnitude, one's complement and two's complement representation. All these are same. All these are same. Now, after all these three representations after understanding all these three representations, we have observed there are some advantages in 2's complement representation. What are the advantages of 2's complement representation? First and most important advantage is 0 is having only one representation. 0 is having only one representation. The first and most important advantage is 0 representation. 0 is having only one representation in 2's complement representation. And one more advantage is there, which is a expanded range. Expanded range. What is that? If you are observing sign to magnitude 1's complement representation using 4 bits, -7 to +7. In 2's complement representation, -8 to +7. Be clear about this. In sign to magnitude and 1's complement representation using 4 bits, the range is -7 to +7. In 2's complement representation, it is -8 to +7. If I'm using 5 bits, be clear about this. Don't remember with respect to only 4 bits. Be clear about the concept. If I'm using 5 bits, the range in sign to magnitude and 1's complement representation is -15 to +15. Substitute n value is 5. Right? In the formula we have discussed, if I'm using 5 bits in sign to magnitude and 1's complement representation, the range is -15 to +15. Coming to 2's complement representation, the range is what? -16 to +15. Coming to 6 bits, if I'm using 6 bits, the range in sign to magnitude and 1's complement representation is -31 to +31. Using 6 bits. If I go with sign to magnitude and 1's complement representation, the range is -31 to +31. In 2's complement representation, -32 to +31. And so and so. 4 bits, -7 to +7 in sign to magnitude and 1's complement. In 2's complement representation, -8 to +7. How many numbers we are representing extra? One number, -8. Coming to 5 bits. What is the range in sign to magnitude and 1's complement? -15 to +15. Coming to 2's complement representation, the range is -16 to +15. How many numbers extra? Only one. Coming to 6 bits. In sign to magnitude and 1's complement representation, the range is -31 to +31. In 2's complement representation, -32 to +31. How many numbers extra? Again, one number only -32. Because -31 to +31 is possible in sign to magnitude and 1's complement. -32 extra in 2's complement representation. That means you may be using 4 bits or 5 bits or 6 bits or any number of bits. It is possible to represent one number extra in 2's complement representation compared to sign to magnitude and 1's complement representation. Right. Once again, advantages of 2's complement representation. First one is what? 0 is having only one representation. That is the first and most important advantage of this representation. Because there was a drawback in those two representations, 0 representation. Now, 0 is having only one representation. And second advantage is expanded range. How much it is expanded? Only one number extra. Irrespective of number of bits, it is possible to represent only one number extra in 2's complement representation. Right. Once again, let me address about 3 representations. Common points: MSB0 positive, MSB1 negative. Second common point is what? Positive number representation. What is it? In 3 representations, positive numbers representation is same. These 3 representations are different for negative numbers only. Right? So, for positive numbers, all 3 representations are same. These 3 representations are different in representing negative number. Right? And after discussions, we observed 2's complement representation is having advantages. What are those advantages? 0 is having only one representation. Second advantage is expanded range. How much it is expanded? One number extra, irrespective of number of bits. You may be using 100 bits. How many numbers extra I can represent in 2's complement representation compared to signed magnitude and 1's complement? Only one. You may be using any number of bits. Comparing with signed magnitude and 1's complement representation, it is possible to represent only one number extra. Right. Rules, similarities, advantages we have covered till now. About 3 representation: signed magnitude, 1's complement and 2's complement representation. Right. Now, as everyone might be getting the same doubt, when I started studying about this also, I got the same doubts. Yes, I'm following the rules, but why these are named specifically 1's complement and 2's complement? When we are coming to signed magnitude representation, yes, sign plus magnitude, clarity is there. What is it here? Signed magnitude representation means sign plus magnitude, clarity is there. We don't question why it is named as signed magnitude representation. But coming to 1's complement and 2's complement, in these protocols, in these rules, nowhere I have used 1's complements and 2's complements. But these are named as 1's complement and 2's complement. Why these are named as 1's complement and 2's complement? Let us justify the name. What we are trying to do? Justifying the name 1's complement and 2's complement representation. Am I audible? Is my screen is clear? Is my video is clear? Any disturbances? Any problems? Right. Thank you. Thank you. Thank you. Yes. Yes. Are you clear with the concepts now? Whatever we have discussed, whatever doubts you have, I'm going to clear. But concepts so far we have discussed. Is it clear? Yes. Similarities. Some people are asking that what is similarity is same thing. What is it? MSB is 1, number is negative, MSB 0, positive. There is one similarity among all 3 representations. And also positive number. Example, if I say plus 5, how do you represent in signed magnitude? Plus 0, 5, 1, 0, 1. Right? And what about 1's complement? No doubt 0, 1, 0, 1 only. Because MSB should not be 1. If MSB is 1, becoming negative, MSB should be 0. And what about remaining? You need to get 5. That means 1, 0, 1. And in 2's complement also same. MSB should be 0 because number should be positive. And how to get 5? 1, 0, 1. That means 0, 1, 0, 1. So all positive numbers representation is same in signed magnitude, 1's complement and 2's complement representation. Right. Right. Now, let us justify the name why these are called ones complement and twos complement representations. First, let us verify with respect to ones complement. And try to reply yourself when I'm writing, when I'm asking. It may not be possible to type by everyone. So ones complement, we are in ones complement representation. That means we are using weights. MSB weight is minus of 2 power n minus 1 minus 1. And remaining bits positive weights. That means using 4 bits, what can be that? Minus 7 plus 4 plus 2 plus 1. If I say 1, 0, 1, 0, what will be the decimal equivalent in ones complement? I'm not saying that take ones complements of this. I'm asking what is the decimal equivalent of 1010 using minus 7 plus 4 plus 2 plus 1. If I'm calculating, minus 7 plus 2 is minus 5. Now, if I take ones complement of this, I'm very much clear how to get ones complement. What is that? Complementing all the bits 0, 1, 0, 1. What will be the decimal equivalent with ones complement rules? 0 plus 4 plus 0 plus 1 plus 4 plus 1, it is plus 5. Is it clear? If I'm taking ones complement, it is giving plus 5. 1010 with ones complement protocols, it is minus 5. If I'm taking ones complement, it is giving plus 5. So with ones complement rules only, if I say representation is 0110, what is the decimal equivalent? Plus 6. Plus 6. Am I right? 0 plus 4 plus 2 plus 0 plus 4 plus 2 is plus 6. If I take ones complement, what is here? 1001. Then what we get here? 1 into minus 7 plus 0 plus 0 plus 1. Minus 7 plus 1, it is minus 6. By this time, you might have understood why it is named as a ones complement. If I'm using that rules, if I have a positive number, if I want to get equivalent negative number, I don't need to represent again. If I take ones complement, I'm getting same magnitude with opposite sign. If I'm taking ones complements, I'm getting same magnitude with opposite sign. If it is positive number, if you are taking ones complement, with ones complement rules, it is giving negative number. If it is negative number, taking ones complement, with ones complement rules, it is giving positive number. To get opposite sign with same magnitude, I don't need to represent again using rules, just take complements. Right? So, let us see, is it correct with respect to 2's complement also? If I take 1010 itself, what is the decimal equivalent? Now, rules is what? Weights are changing. Minus 8 plus 4 plus 2 plus 1. Minus 8 plus 4 plus 2 plus 1 weights means minus 8 plus 2. It is minus 6. Right? Minus 6. If I take 2's complements of this, what is it? 0, 1, complementing all the bits. I hope you are using the way we have discussed to get 2's complement. What is it here? Starting from LSB, 0 as it is, 1 as it is, complementing remaining bits. What is it here? Till the first non-zero LSB as it is, remaining bits complemented. Right? So 0, 1 and remaining bits complement. What can be the decimal equivalent here now? Plus 6. Am I right? Using same protocols of 2's complement representation. So 0 into minus 8, 0, plus 1 into 2, 2, plus 1, sorry, plus 1 into 4 is plus 4, plus 1 into 2 plus 2, plus 0. That means plus 4 plus 2 is plus 6. Right? Now, if it is 0, 1, 1, 1, what can be the decimal equivalent? In 2's complement representation, what can be the decimal equivalent? It is plus 7. If I take 2's complement of this, what we get here? 1, 0, 0, 1. What is the decimal equivalent? Minus 8 plus 1, it is minus 7. Yes, once again, in 2's complement representation also, it is satisfied. What is that? Positive number is there in 2's complement representation. If I take 2's complement of that, it is giving negative number. If it is negative number is there, if I take 2's complement of that, it is giving opposite sign number, right? So, if I would like to get a opposite sign number with same magnitude, I don't need to represent again. Simply taking complements, it is satisfying. Right? Representations are giving opposite sign number when we are taking complements. Yes. Justifying the name, why these are called 1's complement and 2's complement representation. Yes, yes, yes. I'm coming to that only. Right. If I consider 1 0 0 0 4 bits in 2's complement representation 1 0 0 0, what is the decimal equivalent? Minus 8. Am I right? It is minus 8. 1 0 0 0 using 4 bits in 2's complement representation, decimal equivalent can be minus 8. 1 into minus 8 plus 0 plus 0 plus 0. Yes, minus 8. If I take 2's complement of this, what we are expecting? Plus 8. Yes, let me write 2's complement 0, 0, 0, 1. Already we know this. 1 all zeros 2's complement will be giving 1 all zeros only. Correct? 1 all zeros is giving 2's complement is 1 all zeros only. So here we get have to get plus 8, but we are not getting plus 8. Again it is giving minus 8. Again it is giving minus 8. Yes or no? We are expecting plus 8, but it is not giving plus 8. It is not giving plus 8. It is giving again minus 8. According to the rules, it has to give plus 8. But it is not giving plus 8. Why? Plus 8 cannot be represented using 4 bits. Because the most positive number using 4 bits is what? Plus 7. It is out of range. Plus 8 is out of range of 4 bits. Plus 8 is out of range of 4 bits. Then we can say there is a overflow. What is it here? Overflow. When do we get overflow? When carry is there? No. When we are dealing with unsigned numbers, when you're adding two numbers, when you are getting a final carry out of carry, then we are saying that overflow is there. When we are dealing with the unsigned numbers, but here that statement is not correct. Getting carry is overflow. No. What is it here? When do we get overflow, or what is overflow exactly is the result is what? Plus 8. That plus 8 cannot be represented using 4 bits. Now we say overflow is there. What do you mean by this? If the result of arithmetic operation cannot be represented using same number of bits, then there is a overflow. Overflow. Try to understand point correctly. Overflow. Some of you might have studied it in 8086 overflow flag. Right? So overflow is there, or we can say overflow is occurring. When can we say overflow is occurring? When number of bits used is not sufficient to hold the result or to represent the result. Then we can confirm there is a overflow. Point should be understood correctly. If number of bits used is not sufficient to hold the result or to represent the result, then we say overflow is occurring. Then we say overflow is occurring. Once again, try to understand definition. If number of bits used is not sufficient to hold the result or to represent the result, then we say overflow is occurring. I will give you clarity about overflow, including Boolean expression for overflow. I will discuss later. Until that, please hold on. At this moment, try to understand definition of overflow. What is definition of overflow? If number of bits used is not sufficient to hold the result or to represent the result, then we say overflow is occurring. Then we say overflow is occurring. Because result is what? +8. But +8 cannot be represented using 4 bits. That is the reason we are confirming there is an overflow in this condition. It's a drawback. It's a problem. The problem should be rectified. Let us see what is the idea to rectify the problem. I hope you are following till now what I've been conveying. So here result is +8, but +8 I cannot represent using 4 bits. 4 bits range is -8 to +7. But result is what? +8. +8 cannot be represented using 4 bits. That is concerned as a overflow. That is considered as a overflow. It's a problem. The problem can be eliminated by understanding one more important properties of these. What can be that? Let us see. Right. See. 2's complement representation. Follow correctly. Don't deviate. Focus on my words. Focus on what I'm writing. For example, in 2's complement representation, 1 0 1 0. Can you help me? What can be the decimal equivalent? We are in 2's complement representation. The weights are -8 +4 +2 +1 using 4 bits. Then what can be the value? -8 +0 +2 +0. Any doubt in that? I think no doubt. -8 +2, decimal equivalent is what? -6. In 2's complement representation, 1 0 1 0 is representing -6. Clear? Now, if it is 1 1 0 1 0, what can be the decimal equivalent? So it is in 2's complement representation only. The representation is 1 1 0 1 0. What can be the decimal equivalent? If I'm using 5 bits, what is the weight of MSB? -16 -2 power 4, sorry, 5 - 1. That means -2 power 4, -16. It is -16. Next, +8, +4, +2, +1. All the remaining bits are having positive weights except MSB. MSB is having negative weight. Weight is -2 power n-1. What is n? Number of bits. Now I am using 5 bits. When I am using 5 bits, weight of MSB is -2 power 5 - 1. -2 power 4, it is -16. 1 into -16 plus 1 into, what is the weight? 2 power n-2. 2 power 5 - 2. It is 2 power 3. It is +8. Next, +4 +2 +1. So what is it here? -16 +8 +0 +2 +0. What is the value of this? -6. Correct. It is -6. If it is 1 1 1 0 1 0, what is the decimal equivalent? What is the decimal equivalent? What is it now? MSB -32 +16 +8 +4 +2 +1. MSB only having negative weight. So 1 into -2 power 6 - 1. That is -2 power 5. What is the value here? -32. Next bits, all the remaining bits are having positive weights. Then -32 +16 +8 +0 +2 +0. What is the value? -6 again. Then 1 1 1 1 1 1 1 1 0 1 0. What is the decimal equivalent? 6. Right. Let me consider one positive number also. 0 1 1 1. What is the value? No doubt it is +7. 0 0 1 1 1. What is the decimal equivalent? +7. 0, 0, 0, 1, 1, 1. Decimal equivalent is what? Plus 7. 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1 is plus 7. Right? What we are observing? MSB is 1, number is negative. Extending that one, decimal equivalent is same. MSB 0, number is positive. Extending that 0, value is same. Which one we are extending? MSB. What is MSB? Sign bit. In all three representations, MSB is having a significance. What is that? MSB 0, number is positive. MSB is 1, number is negative. That is representing sign of the number. So if you are extending that MSB, which is the sign bit, value is not changing. Decimal equivalent value is not changing. When you are extending MSB in 2's complement representation, extending MSB, which is sign bit, decimal equivalent is not changing. It is named as a sign extension property. What is it here? Sign extension property. If the numbers are in 2's complement representation of signed numbers, if you are extending that signed bit, which is MSB, value is not changing. Whenever it is required to represent using more number of bits, now you need to extend with MSB only. Already I discussed this point while converting B to B power n by grouping n number of digits. If a number of digits is not sufficient for grouping, you are appending zeros because we are in unsigned numbers. Coming to signed numbers, if it is in 2's complement representation, if it is required to extend the bits, if I append zeros for negative number, it is giving a wrong value. Then what should I do? Extending with MSB. For negative numbers, as MSB is 1, extend that 1. For positive numbers, MSB 0, extend that 0. It is required to extend with the signed number, signed bit. Right? Because it is having sign extension property, or it is obeying that sign extension property. What is it here? MSB is 1, extending 1, value will not be changing. Whenever it is required to represent the same number using more number of bits, how can I represent? Simply extending with MSB. The same number without changing the value. If I would like to use more number of bits, then simply extend with MSB. Right? So, simple thing. A number is in 2's complement representation. I want to represent same number using more number of bits. In such cases, no need to worry. How do I represent? No, simply extending with MSB. Why I have been mentioning as MSB? It may be positive, it may be negative. If it is unsigned numbers, appending zeros is applicable always. What do you mean by unsigned numbers? Only positive numbers. When we are dealing with only positive numbers, extending zeros was applicable. But when you are dealing with signed numbers, both positive as well as negative numbers we have. When we have both positive as well as negative numbers, which are signed numbers, so whenever it is required to represent using more number of bits, in such cases, extend with signed bit, which is MSB, which is MSB. Yogasri 1010 is minus 6 in 2's complement representation. 1010 is minus 5 in 1's complement representation. Why you are getting doubt now? Go with the weights we have discussed. Weights are different for 1's complement representation and 2's complement representation. Right? That is the reason I told you already. Knowing complements is different, right? Using rules of this representation is different, right? Please focus on my discussion. Don't make a short notes of my discussions, right? Now itself. Later you can do. Understanding concepts, you can make a short note. Now itself, by leaving some concepts, only grasping some concepts, by understanding some concepts, instead of understanding everything, if you are following, you will be doing a mistake. 1010 is minus 6 in 2's complement represent. How? Weight of MSB is what? Minus 8. Next, plus 4, plus 2, plus 1. Weights using 4 bits. Minus 8 plus 2 is minus 6. The same. For example, if it is in 1's complement representation, 1010 is in 1's complement representation. 1010 is there in 1's complement representation. Can you say what can be the value? Weight of MSB is what? Minus 7. Next, plus 4. Next, plus 2, plus 1. Weights. But weighted values, minus 7, plus 0, plus 2, plus 0. What is the value? Minus 7, plus 2. It is minus 5. Why am I getting minus 5? Weights are different in 1's complement representation. Rules are different in 1's complement representation. Right? It is minus 5 because I'm adding minus 7 plus 0 plus 2 plus 0. Because weights for respective positions is minus 7 plus 4 plus 2 plus 1. It is minus 7 plus 2, it is minus 5. Yes. If it is 11010, I'm verifying whether it is applicable sign extension in 1's complement representation or not. I'm trying to convey whether it is possible to have a sign extension in 1's complement representation or not. If it is 11010, you need to mention what is the weight of MSB now? Minus 15. Substitute minus 2 power n minus 1 minus 1 minus 2 power 5 minus 1 minus 1 minus 2 power 4 is 16 minus 1 is 15. MSB weight is minus 15. What about next bit? Plus 8, because remaining all the bits are having positive weights. Plus 8 plus 0 plus 2 plus 0. What is the value now? Minus 15 plus 10. It is again minus 5. If it is 111010, what can be the decimal equivalent? Now it is minus 31. Please calculate the weights using formula which I have given. Minus 31 plus 16. Next bit weight is 2 power n minus 2, which is positive. 2 power 6 minus 2. It is 2 power 4. What is it here? Plus 16. If I am using 111010, 6 bits I am using, MSB weight will be minus 31. Next to plus 16, plus 8, plus 4, plus 2, plus 1. Weights. But weighted values are minus 31, plus 16, plus 8, plus 2. What is the value? Minus 5. Once again, if I am extending this one multiple times, the value will be same. If it is 0110, what is decimal equivalent? Plus 6. If it is 00110, again it is plus 6. If it is 000110, also plus 6. If I write 0000000110, also plus 6 only. Plus 6 only. That means in this 1's complement representation also, extending MSB or extending sign bit, it is giving same value. In this 1's complement representation also, extending MSB or extending sign bit, decimal equivalent is same. It is named as a sign extension property. In 2's complement and 1's complement representation of signed numbers, extending sign bit, decimal equivalent value is not changing. Whenever it is required to represent using more number of bits in these two representation, you can extend with MSB. You can extend with the sign bit. Harshavardhan, why are you applying the 2's complement rules in One's complement. Why do you want to take right? What is that here? Two's complement method. Least significant zeros. शुभम वेट पूरा समझ में आएगा. Shweta, I'll discuss about overflow in detail later. At this moment, what we need to understand is if number of bits is not sufficient to represent the result, then we say overflow is occurring. Right? So once again, what is discussed in this slide, in this frame, is a sign extension. What is it here? In two's complement and one's complement representation of sign numbers, extending sign bit, which is MSB, decimal equivalent value is not changing. Decimal equivalent value is not changing. Harshavardhan, how to get one's complement? Complementing all the bits. Why are you applying two's complement rules which we observed in one's complement? One's complement we can get by complementing all the bits. Why are you observing that LSB is 0 and 0 as it is, 1 as it is, and complementing? That is rule for getting two's complement. Please understand in the right way. Right. So finally, what is discussed in this slide is a sign extension problem. What is that here? Extending sign bit, which is MSB, decimal equivalent value is not changing in one's complement and two's complement representation of signed numbers. Whenever it is required to represent using more number of bits, in such cases, just extend with MSB. If it is confirmed numbers are in two's complement and one's complement representation of signed numbers, whenever it is required to represent using more number of bits, simply extend the MSB. See, there was a question in ESC objective, IES objective. Yes, Arpit, will be discussed. Don't worry. I'll take care of all the concepts. Right? Banavat Sai, please wait. I'll take some examples, then I'll help you in writing. How do we write the numbers? I'll give you clarity. Please wait. Right. So here, what we have discussed, sign extension. Extending sign bit, decimal equivalent is not changing. Extending sign bit, which is MSB, decimal equivalent is not changing. Decimal equivalent is not changing. Extending MSB, it is not changing decimal equivalent. That is sign extension problem. So let us go back to the previous discussion. What is it here? We observed a problem. What is it? Overflow problem. So 1,000 is a -8. 1,1,000 is also -8 only. Right? If I take 2's complement of this, what we get? 0, 0, 0, 1, complementing next bit. What is the value of this in 2's complement representation? +8. Confirm, it is +8. +8 can be represented using 4 bits. Yes. Plus 8 cannot be represented using 4 bits. Plus 8 can be represented using 5 bits. If I'm providing sufficient number of bits, it is following rules correctly. Otherwise, it gives a wrong result. If number of bits itself is not sufficient, how can you expect correct result? Because there is an overflow. Why? It cannot hold the result using same number of bits. Then we say overflow is there. When overflow is there, we cannot expect correct result. Right? So, earlier with 4 bits, we are trying to get plus 8. It was not possible. That is confirmed as an overflow occurrence. Result cannot be represented using same number of bits. Is confirmed as overflow occurrence. If you are providing sufficient number of bits, it is giving expected correct result. Yes, -8 can be 1,000,000. The same -8 can be written as a 11,000,000. With that, if you are taking 2's complement, yes, we are getting expected result plus 8. Expected result plus 8. Right? The problem was there. The problem is rectified. What is it here? We observed 4 bits is not sufficient to represent plus 8. That is the reason the same -8, if I represent using 5 bits, then it is a, are you able to understand it is -8, -16 plus 8. When I'm using 5 bits, MSB weight in 2's complement representation is -16 plus 8 plus 0 plus 0 plus 0. It is -16 plus 8. Value is -8. -16 plus 8, it is -8. So, if I'm taking 2's complement, no doubt it is 0 plus 8 plus 0 plus 0 plus 0. Value is what? Plus 8. That is expected. It should be plus 8. Yes, it is plus 8. Yes. Manisha, not required this, sir. If you are interested, you can take. And try with this, sir. You'll be getting same answer. Manisha. Yes. Yeah. I'll give you a chance to discuss doubts. There, please, you can ask. So for today, let me wind up here and let me know your questions, your doubts. I would like to answer your doubts. One by one. Sahil.
Good evening, sir.
Yes, Sahil.
Sir, in signed magnitude representation, we have rule MSB 0 equals to positive and MSB 1 equals to negative.
Yes.
But sir, in first one's complement, sir,
Huh?
sir, 0 0 0 0 equals to positive 0 and 1 1 1 1 equals to negative 0. So why we are taking positive 0 for,
As we are getting two representations for the values is same.
yes, the value is
Right.
same, but sir,
So the rules is what? MSB 0 number is positive, MSB is 1 number is negative.
sir, same rule will follow in one's complement also.
Yes.
But sir, in, in this we have minus 7 4 2 1. Sir, we are using this now.
Yes.
So then why we are taking sign convention like this?
Please be clear with your question and I'll try to help. Please.
Yes, sir.
These are rules which we are following. And here, these are rules. With these rules also, finally we are observing this is there.
Okay.
And here also. Then what is your doubt? Please.
So 10F. Sir.
What is it?
10F. Sir.
10F. Okay.
So here we have 1 1 1 1 equals to minus 0 and 0
Yes.
0 0 to positive
No,
0.
I'm saying this is a 0. But this is also 0. How can I differentiate these two?
Sign convention.
That's what,
0.
that's what I've used, right?
Sir, why we are taking 0 0 0 equals positive 0 and 1 1 1 equals negative 0? You say interchange be.
In this also, what is observed finally? MSB is 1, negative. Correct?
Oh, okay, sir. Okay.
It is positive. Correct?
Okay, sir.
Right? Okay.
Thank you, sir.
Thank you. Thank you. Ashish Kumar.
Hello, good evening, sir.
Yeah, good evening. Very good evening. Tell me.
My doubt is from previous class,
Okay.
where you have given us a question under root of 41 is equals to 5 and base of x, where first we converted the whole thing into x and then we calculated the answer. But here, sir, if we are removing the square root from here, then we have to square 5. So 5 square means we have to add 5 times, right?
Yes, sir.
So now my doubt is here that how we just multiplied 5 into 5 as we multiply in decimal.
Because before that itself, we are converting decimal. See, the
Yes.
numbers are converted to decimal, then we are squaring. In the given equation, 4 1 is becoming 4x plus 1. How? We
Okay,
are
sir.
calculating decimal equivalent. What is the 5 decimal equivalent? 5 into x power 0. After confirming number is in decimal, then I'm writing 5 square, which is 25.
Yes, sir. Yes, sir. Sorry, sir.
Right.
Thank you.
Right.
Yes, and I got it. Sir. I got it.
Right. Thank you.
Thank
Thank you.
you.
Sahil. Sahil Singh. Sahil.
Hello.
Yes.
Yes, sir.
Yes. Yes, Sahil Singh. बोलिए.
Sir, doubt clear हो गया, sir.
ठीक है. Thank you. Thank you. Ashish Kumar. Ashish Kumar. Annapurni.
Hello, good evening, sir.
Very good evening, ma. Tell me.
So my doubt is from previous class.
Yeah, tell me.
We have a base x, we will be calculating from the quadratic equation, right? To
Yes.
know the x value.
Yes.
If in quadratic equation, if we got x value in the form of imaginary or something in the form of root, what will be the base, sir?
I didn't understand your words, ma. Please elaborate what you are saying.
Okay, if we calculate x through quadratic equation, if my quadratic equation contains an imaginary value
No.
or a root
That is not
value.
possible, right? Then we say no base is possible.
Okay, for an example, if it is root 121 is equal to 11, so what will be the base of that, sir?
It can be any value greater than 2.
Okay, so we cannot predict that I mean, it will be greater than 2.
Yes, it can be any value greater than 2. That means greater than or equals to 3. Check it.
Okay. And the second doubt is when we are converting from any base to decimal, when we are multiplying the fractional part, if our fractional part is repeatedly coming like 4, 5, 4, 5 and 4, 5 continuation,
Yes, we'll be getting.
then what will be the fractional part, or else we will stop until 4, 5 only, or we will be repeatedly going on with that?
That depends on what they are expecting. If it is multiple choice question, you can choose from the options for our exam.
Okay.
Right? If it is a
Okay.
numerical answer question, they have to mention how many digits they are expecting.
Okay, sir. Thank you so much.
Right. Thank you. Sajjan Singh.
Good evening, sir.
Very good evening, Sajjan Singh.
Sir, what's the exact meaning of overflow?
I will discuss more and more about this overflow. Simple thing is, result cannot be held using same number of bits. Result is out of range.
Okay.
If I'm using n bits for an operation, arithmetic operation, in that operation, result is bigger, is out of range. Then we can say there is an overflow.
Okay.
Clear?
Thank you.
Thank you. Thank you. Yes, sir. Manisha.
Sir, good evening, sir.
Yes, ma'am. Yes, ma'am. Tell me.
Sir, in third frame, you have said like two types, like radix
Right.
R and R minus 1 radix, right?
Yes.
In that you
It is not
wrote
radix R. Please, right. It is not radix R and radix R minus 1. What is it here? Radix complements, diminished radix complements of number which is in radix R. For these two complements, number is in radix R only.
yes, sir. Sir,
Right.
but you wrote here means R's complement equal to R power n minus 1 and R minus 1 complement equal to R power n minus R power minus n minus 1. And how did you wrote like this?
Do you want to get derivation of this, sir?
No, sir. Like I didn't understood this expression, so that's it.
Why? What is n you want to know? What is capital N you want to know? Nothing is there to understand. There is a procedure which is giving expected complement. That's it.
Yes, sir.
They won't ask you to write these formulas. That is the reason I didn't talk much about this. That is the reason immediately we shifted to use some methods to get complements. To
Yes.
satisfy all these, if you want to frame a formula, this is correct. I got from one textbook.
Okay.
Right.
Sir,
There
like
is
I
a
did,
derivation for this.
R
That
per
is-
um,
To
R
satisfy this, please. To satisfy these complements, this formula is applicable. That's it.
okay, thank you.
Right. Dinesh Roy.
Hello, sir. Good evening, sir.
Yeah, tell me.
Sir, in page number 2,
Okay. Yes.
frame number 2.
Yes. I mean page
So
number
you
2.
told for the number of solutions, you told that like the value of x must be less than value of y, no, sir.
Okay. Value of x must be less than y. And 8 also must be less than y. That means y must be greater than x, y must be greater than 8. See here, I have written.
Sir, if they're equal x and y values are equal at that time, what will you do?
It is not possible, right? In base 8, is 8 is possible? In base 8, what is possible?
sir.
Up to 7.
Okay, sir. Okay.
Right? Okay.
Okay, sir. Okay. Okay, sir.
Right. Any more doubts?
Sir, in frame number 4.
Page number 4. Okay. Okay.
Sir, for that 8's complement, you told that it must be 0 to 7, no, sir? For 8's
Yeah, I have given
complement.
0 to 7 only, right?
Yeah, for that 10's complement, it must be
0 to 9.
it also must be the below yes, sir.
0 to 9. The digits must be 0 to 9.
0 to 9, no, sir.
Yes, 0 to 9 only, right? 10's complement.
But for 9's complement, it must be like 0 to 8, no, sir.
No. In 9's complement of decimal number also, we can have 0 to 9. The digits are decided by which number system is that?
Okay, sir.
Not with respect to complements. That means,
Okay, sir.
in 7's complement, we have 7. In 9's complement, we have 9.
Okay, sir.
Right?
Okay, sir. In 1's complement, we have 1.
Yeah.
Okay, sir.
So that is which digits are possible is decided by number system which we are using.
Okay, sir. Okay.
Right. Thank you.
Okay, thank you, sir.
Shubham. Shubham Kumar.
Hello, sir. Good evening.
Very good evening. Tell me.
Sir, I want to know, could you give any reference book for digital?
Yeah, I forgot to make a slide. Sure, I'll give you in the next class. Sure. Please wait. I'll give you all the details clearly. Instead of mentioning this name, I'll give you all the details. I'll make a slide before coming to the class itself. Please wait. Right?
Or textbook?
Yeah, textbook.
Okay.
I'll make a slide. Which books and which topics we need to go through that. I'll mention all those. Please.
Okay, sure. Thank you, sir.
I make a slide. I'll make a slide. I'll display that. Sure. Thank you. Yugasri.
Sir, good evening, sir.
Very good evening, ma'am. Tell me.
Sir, yesterday you given one question, sir, 301.23 base 4 equal to
320 divided by 20 equals to 13.1, right?
sir
320 divided by 20 equals to 13.1.
301.23 base 4
301.
0.23
Yes.
base 4
Yeah.
is equals to the
What is the base 7 equivalent, right?
Yeah, yes, sir.
Yes.
In
You are
that
not
question,
getting fraction part limited one, right?
repeated one and one
That's
more,
what,
sir.
someone was asking same doubt. That's what I mentioned. When you are getting such numbers, they won't ask you to write everything because we are in competitive exams. Right? Then what we do? If it is options, we go with the correct option, nearest
Yes,
one. If it is numerical answer question, they mention that how many digits they are expecting in the fraction part.
Okay,
have-
sir.
They have.
And this type of questions, how we have to find, sir? First we have to find base 10 and then we have to find base
Obviously,
7, sir.
we have to.
How we have to find, sir, that type of questions? Sir?
What mean by? Like this is what is that? Decimal to any base to decimal, b power n to b to b power n. If it is not these, remaining is next. What is it here? Decimal to required.
Okay.
If it is not under these 4 cases, then we go with the decimal to required. Right?
Okay, sir. Not only decimal, we can binary system or anything. We can
Anything.
find also.
Anything. What we do
Okay, sir.
first? One number system to another number system. In between, it is not include decimal. It is not b to b power n. It is not b power n to b.
Okay.
The numbers, if it is expected decimal, we know that. Binary to decimal or base 3 to decimal, all this we know. But
Yes, sir.
for example, base 3 to base 7, what should I do? It is
Base to
not any base to decimal. It is not decimal to any base. It is not b to b power n. It is not b power n to b. The reason, what we do?
So we convert.
Calculating decimal to required.
Okay, right. Okay.
Done?
Okay, sir. Thank you, sir.
Thank you. Anyone else is having doubts? Param. Yes, Param.
So first slide.
Okay, going to that. Okay.
Okay. Sir, the question here asked is find the valid solution for that x and y.
Yes.
Right. Sir, we have to replace those x and y with numbers, or just we have to find out what are the possible solutions for it?
So it is not asked what is the values of x and y. It is asked how many number of valid solutions.
Okay.
When equation is given, how many solutions are possible means how many different solutions are, what is the values you consider? When equation is given, number of solutions means, do you think about what is the solution or what is the number of solutions?
Okay, sir. Yes,
Number of
number of
solutions.
solution.
I don't worry about what is x and y values, but how many valid solutions?
Okay. Sir, coming to these values of x and y, we have compared with y, right? Means the number should be less than y. X should be less than y.
Yes.
Sir, when we keep that number, like first one is valid, 1 and 35 is valid. So if we replace that x with 1 and y with 35, then the number will be 10, right?
10.
Above. If we replace that x and y, the number will be 10 to the base 35. It will be.
Why it is 10?
Sir, x value we have find out, right?
No, it is not value. What do you want to substitute here?
The possible numbers.
You want to use this one, right?
Yes.
If you want to use 35 here, here 1 is required. Is it valid now?
No, this is not valid.
That's what we are saying, right?
Sir, in next slide, then we have next slide.
Going to that. Yes.
Yes, sir, we have many possibilities here which can satisfy that thing.
Yes.
Means they are
validating, same.
Sir, like we have 5 and 6, which is not valid.
Yes, it is not valid. Reason is these two conditions should be satisfied.
Okay.
So y must be greater than x, y must be greater than 8.
So means we don't have to replace those things, right?
No.
Just we have to check those conditions.
Validate, that's all.
Okay, validate. Okay, fine, sir. Thank you.
Thank you. Rohit Rajendra.
Hello, sir.
Yes.
Yes, sir, in 4F, sir.
In 4F. Okay.
Sir, in first problem, tens complement, sir. Can we append or remove zeros, sir?
Extra.
Yes, sir. In 10 complements.
That
first-
depends on complements you need in how many number of digits.
Sir,
That we are going to understand when we are applying complements for subtraction.
Okay, sir.
That depends on what you require. Depending on that, in the given number, we can append zeros and then take complements.
Sir, means they give in question, no, sir, like that.
No. Yeah, you will understand. Just wait, please.
Okay, sir.
Please wait. You will understand.
Sir. In the digital form, sir, 0 and 1 only right now, sir.
0 and 1 only.
Then how to
Here,
this?
the concepts we are understanding because they have been framing questions based on this also in objective exams.
Yes, sir.
In binary, in digital, we are using zeros and ones only.
Yes, sir. Sir, then this point decimal, how can they represent, sir?
Every number we are able to represent in binary, right?
Okay, sir.
But in binary, we are representing. Even your face, your picture, everything we are storing in ones and zeros only.
Okay, sir.
Right? Your audio, your voice, your face, your picture, everything will be stored in ones and zeros.
Yes, sir.
Everything is converted to binary and stored.
Yes, sir. Means this and fraction also converted, no, sir?
Yes.
Fraction. Okay, sir. Thank you.
Ravi Teja.
Hello, sir.
Yes.
Sir, in the third slide, sir.
Yeah. Yes, third slide. Okay.
Can you explain that formula, sir? R's complements.
What you want me to explain that? To get
Sir,
this value, to get these values, they have fixed this is a formula.
Okay.
There's no derivation for this.
Sir, for R's complement, we done that R minus 1's complement and plus 1, sir. We done.
Yes.
But in the formula, I found that R's complement equal to R to the power of n minus n.
Whatever that addition you are doing should be in respect to radix. What you're doing here, you are doing with respect to decimal. No. You need to do in the respect to number system. The adding one also should be in respect to number system.
I can't getting. I'm not getting.
Yeah, that's what I'm saying. Just take an example, substitute in this, get the value and add one. Are we getting same or not? Verify. Because always we compare our results with the decimal. So here instead of decimal, what you do, take a number in radix 3 or 4 or 5, your wish. In that calculate at R minus 1's complements. Using this or using our method. Then add one to that and calculate from this also R's complement. Adding one you verify and get whatever you are getting with this formula also you are verifying. Then those two must be matching. That's it.
Okay, sir.
Right.
And then yesterday's problem, sir. Root 41 equal to.
Yeah, root 41, not 41. Root 41 equals to 5.
Under root 41 equal to 5, sir. You should do the
Not 41. Ravi Teja, listen. It is not 41, it is 41. Please, after my class, at least follow the rules.
Okay, sorry, sir. Root 41 equal to 5 is the basic, sir.
Yes.
Sir, in the power, if we get that 1 3 or 1 2, can we apply that 4x that x value in the power also?
In the power also.
Yes.
We have to.
We have to apply that 4x that x value, x to power of 0, x to power of 1, x is like that.
Right.
Okay, sir. Thank you, sir.
Triveni. Triveni.
Sir, in sign magnitude representation, yes, MSB plus n minus 1 bits is there, right, sir?
Yes, yes.
Yeah, in n minus 1 bits, we have taken 2 power 0.
Yes, same weights. Whatever the binary weights we are using, 2 power 0, 2 power 1, 2 power 2, so and so.
Oh, we don't take any 8 power 0 like that. We don't do like that, sir.
What is that?
Because previous in one's complement, you weights for.
One's complement rules is different. Two's complement rules is different.
Yes, sir. Here we give only n minus 1 bits, right, sir?
Yes, n minus 1 bits for magnitude with the true binary weights, which are nothing but 2 power 0, LSB to last bit. When I'm using n minus 1 bits, 2 power 0, 2 power 1, 2 power 2, so on and so, 2 power n minus 2, because I'm using n minus 1 bits.
Okay, okay, sir. Thank you.
Any more doubts? Okay. If you don't have any doubts, see you tomorrow.